Prova, prova. Prova YouTube.
Pronto? Sì. Bene. Buonasera a tutti. Iniziamo la sessione sulle optical communication. Chiedo gentilmente di prendere posto. E il primo intervento della sessione sarà Fiber Sensing Deployed. Sì. The first talk in this session will be Fiber Sensing in Deployed TLC Networks by Pierpaolo Boffi, Politecnico di Milano. You have 17 minutes and 3 minutes for questions. Thank you.
Thank you, Ernesto. Good afternoon to everyone. So this first talk of this session related to optical technologies is quite particular because it's about how to make sensitive the fiber cables already deployed in an extensive way, in particular with a sustainable approach in terms of cost, power consumption, footprint, and so on. So you know very well that the fiber cables already deployed for telecom purposes constitute a real ubiquitous utility to provide internet everywhere, and represent a precious asset for a smart and pervasive monitoring, in particular in our cities. To make sensitive the telecom network can give an added value to the fiber infrastructure with a possible revenue for the operators, the vendors, the fiber owners, and so on. So in this present post-COVID period, an acceleration in FTTH rollout is taking place, and also the global fiber market size is expected to further increase in the next decade. And a fiber cable, so a fiber cable deployed in our cities, sensitive to many different parameters, can be very, very useful for many applications. For example, for road traffic monitoring, in order to check the car speed, the car quantity, the congestion, and so on. It can be useful to monitor the structural vibration modes of the buildings already FTTH connected to the access network, in order to understand the rise of a damage, a structural damage of the building, and also for an early warning of earthquake. A sensitive cable can be useful for surveillance of the safety of facilities such as motorways, railways, and so on. And finally, it can be very useful to monitor the integrity of the fiber infrastructure itself, because nowadays the main OPEX is spent in the physical maintenance of the fiber. So we have many, many different optical solutions able to make sensitive the fiber cable. For example, solution based on the backscattering in the fiber, for example, the Brillouin sensor, the DAS, and so on. So these are very, very effective solutions, assuring a good accuracy, a good resolution, but you pay a price in terms of cost, complexity, complexity in DSP processing, data acquisition, data storage, and so on. So nowadays, this kind of solution are used, for example, to monitor the oceans, for example, by using the submarine fiber telecom cables deployed in the seafloor in order to monitor storms, the movement of ships, but also the passage of whales. This is very nice application, but to understand the effectiveness of this kind of technique. So on the other side, another possible solution, very promising, is the exploitation of the coherent detection. So you know that coherent detection is already installed in the modern telecommunication systems in order to detect multi-level modulation formats. And so we can use the tracking of the state of polarization in order to deduce some information regarding the environment. This solution is convenient when you have a telecom system with inside the coherent detection. And you see in this case, in particular, an application for transoceanic fiber sensing by exploiting the transoceanic fiber cables to monitor the earthquakes. So you understand that this is a hot topic in telecommunication this moment. And for this reason, inside the program Restart, there's a focus project, Sensing Net, devoted to the research, analysis, comparison, and experimentation of the different optical techniques able to make sensitive the already deployed fiber network in the different scenarios. So starting from the backbone network, the regional network, and in particular in Work Package 3, the scenario is the metropolitan area network and the access network. This is a particular scenario because, of course, here there's a real challenge to give sensing capabilities to fiber cables deployed in a pervasive way, but not supporting high cost and high complexity. So we have to find a sustainable solution, cost-effective, energy-efficient, transparent to telecom data, and with a reduced complexity in DSP processing. So I would like to present you a possible solution for this kind of scenario, a solution based on an interferometric scheme, very simple, with a very simple implementation, and ideal to achieve an integral measure, for example, of elongation, vibration modes, structural perturbations, and so on. So let's start considering a multi-fiber cable. So we take into account two fibers inside the cable in order to build a so-called Michelson interferometer. What is a Michelson interferometer? It's constituted by two fibers, a sensing fiber and a reference fiber. So usually the reference fiber is isolated with respect to the sensing area to be monitored. The peculiarity of the proposal, of our proposal, is to take the two fibers of the interferometer inside the same cable. So all the strong noise accumulated by the cable due to the hostile environment where the cable is installed, for example, under a road. So this strong noise is cancelled out because it is a common mode noise. So of course, also the reference fiber is affected by the perturbation to be monitored, but we demonstrated that just a slight difference in the geometrical arrangement of the two fibers inside the cable is enough to reveal this perturbation and not to cancel it. So the implementation is very simple. So we can use just two mirrors, terminating the two fibers for sensing, special mirrors, and at the receiver side, a 3x3 coupler in order to achieve a passive homodyne demodulation without the necessity of coherent detection. So, of course, This implementation is possible when you have two dark fibers inside your cable, but if you don't have availability of dark fibers for sensing, you can use also different bands, optical bands, for example, the O band for sensing and the C band for data transmission, telecom data transmission, or also the WDM grid, devoting one wavelength for sensing and the other wavelengths for the data transmissions. So I would like to present you an example of this kind of approach. In case of a telecom multi-fiber cable deployed along a railway, and in this case, the cable is sensitive to the traffic and is able to monitor also the integrity of the railway itself. So the field trial was constituted by 4 kilometers of railway in the north side of Lombardia near the Lake Iseo. And we used a telecom cable, a multi-fiber, 48 fiber cable deployed by an Italian operator in a conduit under the sidewalk running along the railroad tracks. So 2 fibers are devoted in this case to sensing, and the other fibers are available to transport the telecom data, and they are connected to other fibers at the station terminal. So, of course, the cable is sensitive to the passage of trains. You see the acquired signals. It's possible also to understand the direction of the train, because we achieve similar shapes but reversed in time. And the cable is sensitive also to other events, for example, the passage of a car over a railroad crossing. So you see the typical 4 peaks trace. The 2 first peaks are related to the contact of the tracks with the front wheels of the car, and the other 2 peaks, the contact with the rear wheels of the car. And we can deduce from the trace the speed of the car. We can recognize a car from a truck. So we have information regarding the traffic in this case. But the cable became sensitive also to a lot of other events. For example, dangerous events for the safety, the integrity of the railway, such as the fall of a rock. So you see the acquisition of rock falls. Of course, a rock fall is a dangerous event, so we have a trigger in order to have an alarm and to stop the train. So the sensor is working in this case as a warning tool. So the implementation is very, very simple. So we use off-the-shelf components and devices typical for telecommunication applications, such as a standard laser source with a line width of 1 megahertz, the receivers with a limited bandwidth. So a very, very simple implementation. So I would like to underline that this kind of approach is exploiting an already deployed cable. So we don't know a priori anything about the cable. We don't know the position of the 2 fibers inside the cable. So it's impossible to choose a priori the fibers. So it's not possible to know a priori the sensitivity of the sensor. So machine learning can be useful in this case to support the measurement in order to achieve a better classification of the events and to discriminate in particular the dangerous event from noise. And you see an example of application of a neural network to this kind of measurement. And you see the true positive rates is 100%. So this means that the dangerous event is always recognized. So it's possible also to achieve the localization of the event. We have to arrange the scheme and the configuration by achieving 2 different interferometers. For example, one operating in clockwise direction and the other one operating in counterclockwise direction, or by using 2 wavelengths. And we achieved 10 meters in resolution by using, for example, an acquisition at 20 megasample per second, so a very, very simple acquisition. So this kind of approach matches very, very well also with the exploitation of the so-called passive optical network deployed in our cities. So in particular, it's possible to monitor the buildings already FTTH connected to the PON in order to detect their vibration modes and a failure in the structure of the building. So in this case, we use two final outputs of the last splitter of the PON, not for the ONUs, but for sensing, with two fibers operating as sensing fiber and reference fiber. The sensing fiber is laid on the structure of the building, FTTH connected to the PON, and a peculiarity of this kind of solution is that the feeder fiber does not introduce any kind of noise because the sensing signal in phase is converted in intensity in the last splitter. So this means that the feeder fiber can be also many, many kilometers long and doesn't introduce any kind of noise. So the coexistence with the telecom data is assured by using different bands or different wavelengths. And we had a preliminary experimentation in Torino in collaboration with Politecnico di Torino with a fiber cable deployed in Torino downtown, 11 kilometers long. And with this kind of test, we analyze the impact of the splitting rates of the PON over the sensitivity and accuracy of the sensor, and also the impact of the Rayleigh scattering and the Brillouin scattering. And I would like to show you just the coexistence with the telecom data. In this case, we had 10 gigabit per second of telecom data signals in downstream, co-propagating with the sensing signal. The downstream data are in the O band according to the standard, and you see that there's not any kind of impact in the bit error rate measurement. So by using this kind of approach, many buildings, skyscrapers can be connected and monitored simultaneously by the PON. And in this way, they can operate as seismologic optical antennas, very useful in order to check to have an early warning of possible earthquakes in the city, in our cities, in a very, very simple way, with a very, very sustainable approach. So finally, I've presented you a possible interferometric optical solution able to make sensitive the already deployed fiber cables deployed in a pervasive way with a sustainable approach. So we have seen some applications in order to monitor the traffic, the integrity of a railway, or to monitor the vibration of buildings. So this solution is based on a very, very simple implementation with off-the-shelf components and devices. So demonstrating a very, very good synergy between the deployed telecom network and optical sensing. And of course, inside Sensing Net, we would like to continue the activity in order to better understand the capabilities, the limitation and the advantages of this kind of solution. Let me thank many people. From Politecnico di Milano and also from Coerenza, that is a spin-off company of Politecnico di Milano, developing this kind of interferometric sensor for many, many different applications. So thank you very much.
Thank you, Pierpaolo. We have time for quick questions. Is there any question from the audience? Yes.
This is a problem because, as I said, we cannot design the sensor for the have a region, a segment of the link with a high sensitivity and another region with a lower sensitivity. And this is a problem because you want to detect, for example, rocks with different weights and so on. So for this reason, machine learning can be useful in order to have a better classification.
Okay, thank you. Any other question? I have a very quick question for you. You didn't mention what is the typical maximum length of the fiber that you can accept in this type of technique, which is related to the sensitivity.
Okay, so with this particular approach, we checked that at maximum 50 kilometers.
Okay,
50.
Thank you.
No, it's not a solution for longer links.
Thank you again. And I invite the second speaker, who's Marco Santagiustina from University of Padua. And his talk is nonlinear interference noise in Raman amplified WDM systems. Marco, I recall you have 17 minutes for the talk and 3 minutes for discussion.
Thank you. Thank you very much. So this work is a collaboration between University of Padova and the University of L'Aquila. So let me just briefly outline my talk. A brief introduction about the motivation of the study, then showing this extension of an existing model for nonlinear noise, and then I will show some numerical simulation derived from the model. So when we have a wavelength division multiplex system, we have several channels transmitting, and the signal traveling on different wavelengths travel at different speeds. And therefore, during propagation, there is a what we can call a collision among the pulses. And of course, during this collision, what can happen is that there is an interference, which is not due to linear effects, but to nonlinear effects. In a previous model derived by McCodson and other co-authors, a model was derived to calculate such effects on the constellation. And in this derivation, finally, one can calculate quantity, which is the x 0mm, which is called the collision integral. In their derivation, however, they have taken a few assumptions, very important assumption. One is that the signal amplitude are constant, which means a perfect compensation of losses along the fiber. And also they were assuming high dispersion. In this case, they obtain an analytical solution. However, we are going to consider a different scenario in which we have a so-called Raman amplified WDM system. When you inject a high power pumps inside an optical fiber through this Raman effect, you can achieve a certain gain. And in particular, it's very interesting to exploit several of these pumps, which enable to create a gain which is essentially can be equalized over the different wavelengths, as shown in the right bottom picture. However, of course, to calculate the evolution of the pumps is not an easy problem because it's a nonlinear interaction too. And in fact, what we can show from the picture, the plot on right-hand side on top, we see that pumps can also exchange power among them, and therefore their behavior is different pump by pump. In this particular case, we are showing the evolution of co-propagating pumps or counter-propagating pumps. So the equalization is also an interesting problem. What we have done in this work was to use a machine learning approach in order to calculate the optimal solution regarding the pump wavelengths and the pump powers at the input in order to achieve the flat gain at the output. In particular, our machine learning approach is based on using the model itself of Raman propagation among the pumps, which is shown here, which is a very well known model describing the evolution of the powers of this continuous wave. So what one can do is to have the target gain, G. You have the neural network, which initially can be randomly set, giving at the output the pump powers and the wavelengths of the pump power of the pumps. These are given directly to the model, which finally returns the predicted gain. Then, by comparing the target gain and the resulted gain, and trying to minimizing their difference, you can modify the neural network such that finally, after several iterations, you can reach the final result, which is actually the inverse function of the Raman model, which is, as I said, is a nonlinear model. So regarding the evolution of the average power of each of the signals, WDM signal, one can show, therefore, that in this scenario, the assumption of having a constant signal amplitude, of course, is not there. There is an evolution. Here, there are three cases. The pumps are co-propagating with the signal or counter-propagating, or some are co-propagating and other are counter-propagating. Depending on this different situation, you can indeed, at the end of the link, try to set a certain gain, which is equalized or almost equalized for the different channels. However, the evolution is very different. Moreover, with such short distances, order of 80 or 800 kilometers, you cannot assume the assumption of high dispersion using the previous model. So what we did was to extend the previous model. We use a couple nonlinear Schrödinger equations, and this model is going to account for the cross-phase modulation, which is the effect causing this nonlinear noise. We had also included in the model another nonlinear term, which is the Raman interaction between different channels. The model also includes polarization multiplexing, so this model is a vectorial model. And of course, we included the evolution of the different signal using different configuration of the pumping scheme. The model is also able to return another important contribution to noise, which is the amplified spontaneous emission. So in this, the only change with respect to the previous model is essentially to consider inside the integration of the collision integral a term which is FB, which in case of perfect compensation, which is on the plot on the bottom right side, would be equal, while instead, due to the evolution of the different signal, is changing depending on the scheme we are using, co-propagating, counter-propagating, or bidirectional. So the value of the time integral inside this equation, which are the green lines in this plot, would reach a maximum for the certain collision, but as you see, they are actually modulated in real system when you have Raman amplification. The effect between the interference between channels, also due to Raman effect, has been also counted. The integral, the collision integral, is exactly the same. You have to account for a different coefficient, which accounts for the Raman effect instead of the Kerr effect. So finally, putting everything together, you can get an expression for the noise variance of one symbol, which is reported here, in which you have the sum of the different collision integral due to the different collisions along the propagation, a coefficient which accounts for the Kerr and the Raman effects, which is the one in the modulus square, and then effects due to the pump, and mu accounts is a coefficient accounting for the different constellation you're using. So this is, I can skip. So numerical simulation can be therefore realized with this model. And what I want to point out is that you can essentially separate three different properties you have to specify to calculate the different parts of this numerical scheme. In particular, you can set independently, for example, the Raman gain and the number of pumps and the wavelengths given to the Raman optimizer with the machine learning, which returns FB, which is the function giving the average power evolution of all the signal in your WDM. And also it returns the amplified spontaneous emission noise variance. Specifying some fiber properties and some properties of the signal, you can calculate the time integrals, which are necessary then to realize also the full space integral, which returns finally the values of x, which is the collision integral. Finally, some other properties of the signal, launch power and constellation, give rise to the final step. Therefore, this scheme is very flexible because you don't need to recalculate everything if you just change some of the parameters. So let me show some results. This is a plot showing the results of the collision, depending on the collision index, for the co-propagating, counter-propagating, and bidirectional. What is shown here is essentially that in this case, the co-propagating case show a higher value of the collision integral, so more noise, because as shown also in the previous slides, let me show maybe again, as you can see, the strength of this effect is much higher because the signal tends to increase at the beginning of the propagation. Then you can also calculate what is interesting, the impact of the wavelength of the channel of interest. In this plot, we are presenting curves for two sets of input powers, minus 14 dBm input power for the bottom curves and minus 6 dBm for the top curves. Typically, the co-propagating case, as you see, presents higher noise, which is quite, I would say, predictable. What is also shown here is that there is an asymmetry among the different channels. In particular, for most of the schemes, in particular counter-propagating and bidirectional, the channels in the center of the band are much highly affected by this noise. There are a few dB difference with respect to the channels at the two edges. This is due to the fact that those channels have more collisions because they collide with the channels at smaller wavelengths and at the longer wavelengths. While instead, the channels at the edges show less effect from collision. And this is fundamentally something which comes also from what has been shown in this theory. The last formula at the bottom is showing that the collision integral depends on the inverse of omega, which is the separation among the channels. So the larger the separation, the smaller is the effect. This is why finally we could observe that the channel at the edges are less affected than the one in the center. The model, as I said, we have not only the nonlinear noise, but we have also the amplified spontaneous emission that can be calculated too and added to compare, let's say, to the nonlinear noise. In this graph, we can show curves. The ones that are increasing with the signal input power are those related to the nonlinear noise, while instead the other, which are almost constant over the different input powers, are related to the amplified spontaneous emission, which is not changing much along with the signal input power. And we can find the crossover points where the two signal the two noise are comparable, and therefore one is dominating with respect to the other. Putting everything together, we can finally get kind of optimal point of performance, calculating the overall optical signal to noise ratio. In this graph, what we see is that, of course, co-propagating case is performing well at the low powers, while instead the other tools can perform well at higher input signal power. Apparently, one would conclude from this graph that maybe the co-propagating case is better because it shows slightly better performance for smaller input signal power. However, this model, our model, is not accounting for a very important contribution to noise, which is the relative intensity noise. So when you co-propagate a signal with a pump, with a Raman pump, the Raman pump has a fluctuation, a noise, which is transferred to the signal. And this was not accounted in our model and is highly affecting the result. Therefore, this maximum probably is not really achieved in a real system unless you use a very low relative intensity noise source, which is, however, relatively expensive to use. So you can also perform extensive simulation. The previous simulation were actually performed for a total gain of the link, which was actually minus 3 dB. So the difference, the output signal with respect to the input is minus 3 dB. But then you can also select different approaches in which the Raman gain can target even the full compensation. And this is given in this graph from the position of the zero, so the right side of these two graph, one referring to counter-propagating and the other referring to co-propagating pumps. So you can derive the total optical signal to noise ratio and find the optimal position for the input signal power at different target gain for the Raman amplification. So in this work, we generalize a model to calculate a nonlinear noise, in particular in Raman amplified system, including the polarization multiplexing for WDM links. We integrated this nonlinear computation with the optimized equalization for the pumping scheme of Raman amplification, and our model is flexible because if you change one parameter, you don't need to recalculate everything, but in most situations you can easily use the previous calculation also for some different type of link, just changing a few parameters. The further work to be done is going to be to include the calculation of nonlinear of noise, nonlinear and amplified spontaneous emission in an optimization scheme. In fact, what I showed from the beginning is that the machine learning approach was used only to equalize the gain. However, one may also aim to equalize the noise on the different channels, because we have seen that there are differences due to the different type of collision that WDM signal are experimenting. Therefore, this calculation might be included again in the full scheme of machine learning in order to achieve the best solution. So setting maybe the pump powers and wavelengths such that you can somehow also try to maximize to minimize the noise, and therefore to have essentially less effect from all these amplified spontaneous emission and nonlinear noise. Another extension we are going to consider is that to few mode fibers, in which, of course, the interaction becomes very much because you have propagation on several modes, and also the extension to include four-way mixing terms in this calculation. In fact, our calculation is considering cross-phase modulation, one of the nonlinear effects occurring in the fiber, four-way mixing is typically weaker than cross-phase modulation. However, it is particularly important probably for system in which you want to transmit quantum key distribution, because you want to select a channel in which this noise is highly reduced.
Thank you, Marco. Thank you. We have time for one question. Yes, Vittorio, can you speak louder, please?
Scenario, you get some surprise for sure. And then, did you include the Rayleigh-Best scattering? You get some surprise, and I invite you to test in a real system, because the real system also you have lumped losses that it's really difficult to use machine learning. And then, why did you didn't include the cell phase modulation?
Phase modulation is an effect which can be back compensated with some setup.
Okay. So thank you again, Marco. And I recall to all speakers to stay in time. There is a tablet there with timing. And I invite now the third speaker of the session, who is Lorenzo Gilli from Scuola Superiore Sant'Anna, presenting a novel bidirectional optical wireless communication system using photoconcentrators.
Good morning, everybody. I'm Lorenzo Gilli from Scuola Superiore Sant'Anna, and today I will present the development of a novel bidirectional optical wireless system using optical antennas. This is a collaboration with the INNO Institute of CNR in the frame of the Rigoletto project. I start with a brief introduction of optical wireless system. These systems are a communication system that relies on visible and infrared radiation to transmit data in free space. They can be realized designing a simple communication setup where the message is taken by the transmitter as an electrical input and used to directly modulate the optical source. The optical signal is transmitted in free space and received by a sensor, a photodiode usually, and back converted into an electrical domain. This technology can be a valid solution for next generation of communication system, since they can be designed to reach high data rate up to hundreds of gigabits second. They have a very good electromagnetic compatibility with other instruments, other electronic device, and they can rely on a wide license-free frequency spectrum, and they have a very good intrinsic security, since the light can be easily shadowed. The radiation propagation also is easier to manage with respect to radio frequency, and it's possible to realize simultaneously data transmission and ambient lighting, in this case only using visible light. Moreover, with respect to cable system, optical wireless system can be realized with to be lighter and smaller. Another advantage is the high availability of optoelectronic device that are present in the market with a wide range of performance, such as bandwidth, field of view, transmitted power. Usually, as optical sources, we use the laser pixel and LEDs, both in light, visible, and infrared spectrum, and also commercial lighting system based on the LEDs. A sensor is usually used pin photodiode, but it's possible also to use something different like fluorescent concentrator antennas. This high availability allow to have a wide range of different scenarios where this system can be applied. For example, it's possible to realize indoor communication and positioning system using visible light, optical wireless Ethernet connection. This system can be implemented in the underwater environment to realize the optical links between different drones. It's possible to use the system in the frame of Internet of Things and choosing properly in a proper way the device is possible to realize high-speed optical links to use, for example, in data centers. And it's also possible to apply this these systems in space application to connect different satellites or to connect different equipment on board the same satellite. For this project, we are realizing a system to transmit an Ethernet signal over optical wireless. This system should be integrated into an indoor network and should provide a bidirectional connection between the network and the user using a downlink and an uplink. We are designing it to be realized also using a COTS component to improve the reproducibility and to reduce the overall cost. And we also design it to be plug and play. Here is a block scheme of the demonstrator. For the downlink on the transmitter side, we choose a phosphorus white LED connected to a current driver. And on the receiver side, we are going to use optical antennas and a pin photodiode that have as the absorption peak in the visible spectrum. For the uplink, we are going to use an infrared LED, also connected to a current driver. And on the receiver side, we are going to use a photodiode with the peak in the infrared spectrum. To transmit a signal over optical, an Ethernet signal over optical wire, we have to meet the requirement of the protocol. As a first test, we are going to transmit an high definition video compressed using the standard Ethernet 10BASE-T that is Manchester encoded and has a required bandwidth of 20 megahertz. So as a first measurement, we characterize the optical sources. For the downlink, we measure the luminance of the white LED at 2.5 and 0 degree, 2.5 meter and 0 degree. That is the usual distance and configuration in an office environment. And we measure the optical spectrum and the electrical bandwidth, both of the white light emission and of the blue component of the LED. And we perform the same measurement for the infrared LED. So we measure the irradiance at the same distance, the optical spectrum, and the electrical bandwidth. The novelty of this system are the optical antennas that are not usually used in communication for communication purpose. And they are made up of fluorescent concentrators and a photodiode. In the fluorescent concentrators, the layers absorb the incident light and then re-emits photons at a greater wavelength. Here, the waveguide guide this emitted light towards the photodiode. This system allows to have a receiver with a wide field of view and without any needs of precise alignment. We choose two fluorescent concentrators that are based on different organic fluorophores. This object allows to have a high quantum yield and a good overlap with the visible radiation. Here we have on the right the optical spectrum, the emission and the absorption spectrum of the two versions of the concentrators. And in the end, we characterize the optical antennas by measuring the bandwidths, the electrical bandwidths. We use a white LED as an optical source. As we can see, the bandwidths are very low of some few megahertz, so very lower respect to the minimum required bandwidth. And so we design a passive equalizer to be implemented in the transmitter. As a further improvement, it's possible to increase the data rate of the system. This is possible by employing different optoelectronic device with different performance, so with different field of view or transmitted power. It's possible to optimize the transmission setup by using additional elements such as fisheye lenses, and by changing the link architecture. With all this kind of improvement, it's possible to realize an optical wireless system to transmit an Ethernet signal up to 10 megabit second or 1 gigabit second. Thank you.
Thank you, Lorenzo. Very quick. Now we have 9 minutes for questions. Yes, please. Okay. Since we have time, I suggest you go down to ask.
Yes, this could be a problem, but I guess you're talking about overlapping of different signal. It depends on the delay between the signal and the requirement of the protocol that you want to transmit. So it depends on the system that you want to realize.
I could add that in this case, we are rather more focused on making the system robust rather than trying to shrink the best performance out of that. Because this is a preliminary investigation of how to make the system more and more robust. Because, you know, the biggest issue for optical wireless communication is line of sight, accurate alignment, and so on. So this is the first issue you have to solve practically if you want to go for I would not say an alternative to Wi-Fi, as sometimes people say, but a kind of complementary technology with respect to other radio frequency solutions. Any other question? Yes, Francesco, please.
Just a curiosity. You mentioned your white LED has a bandwidth of 10 megahertz in the blue for the blue component.
Yeah, yes.
But you tested just one LED, or you tested several, and you?
No, we test one LED, a commercial version, commercial LEDs, because the purpose is to use commercial components. So we test a white LED, a commercial white LED.
But you know, there's a wide choice of there's a wide choice of LEDs. Maybe you can find
it's
better
true.
performing ones.
It's true, but we want to make the system as simple as possible. So we are not going to we choose. For us, it's better, for example, to use a passive equalizer to improve the bandwidth, and not to choose a very with an LED with a high performance that is expensive or a custom version, for example.
Yes, pre-equalization is already a choice also for the recently approved standard, which is becoming popular. Any other question? No? Okay.
I have a question from remote, if you can hear me. Yeah.
Yes, sure.
Yeah, it's not clear to me the need for the fluorescent concentrator at the receiver side. What is the advantage and what is the conversion efficiency?
Okay, yeah, the fluorescent concentrators are not obviously the best choice. There are more performing object, but this system wants to test the use of this object in optical optical communication. So one of the purpose of this project is to study the performance of this instrument, of this device in optical communication.
Okay. Thank you.
So, no other question? Okay, so let's thank Lorenzo again. And we move to the next talk of the session, which is PIC, Photonic Integrated Component Technologies for Free Space Optical Links by Francesco Morichetti, who will give the presentation online. Thank you, Francesco. You have 17 minutes.
Okay. Thank you. First of all, let me apologize because I was supposed to give this presentation in Bari in presence with you, but my flight was canceled last night. So this is a backup way to share with you my talk. Yes, first of all, just one slide to introduce our group. We are the Photonic Devices Group at Politecnico di Milano. What we do, we work with the design and testing of photonic integrated circuits, different photonic platform, semiconductors, silicon, purified materials, glass, and lithium niobate. And also different possibility of making testing in the lab. And as was mentioned yesterday by Antonella Bogoni, our lab has just affiliated the Restart program. And at Politecnico di Milano, we have a second facility that is Polyfab. Again, this is the second lab that has just affiliated the Restart program. Is a clean room, so is a micro and nano fabrication center. Is an open infrastructure, so this means that anybody from university, research centers, companies can access this fab. There is a policy for accessing, but of course, this is an opportunity to make some technological activity, some fabrication steps in the Restart project. Moving to the focus of my presentation, in the Restart program, we will be working with the photonic integrated circuits in the field of programmable integrated photonics. That basically means to be able to solve equations, to do some mathematical operations with directly in the optical domain. So this is an example. This is just a vector matrix multiplication. And this can be done in the optical domain by building this multi-stage interferometric structure. And this is an activity that we will be carrying out inside the structural project Rigoletto. There are many different applications for programmable photonics. One of these is in the free space communication. So let's consider to have a free space optical link. And one of the main issue in free space optics is, can you hear me?
Yes.
Okay, there is some problem with, I see my presentation frozen. Let's see if I can. Come on. Maybe it is a problem of this video running. Sorry, I tried to restart my presentation and skip that. Let's try to see if it works. So one of the problems with the free space communication is the presence of turbulence in the atmosphere that introduces scintillation of the optical beam. And one strategy to tackle it is to use an array of optical apertures, let's say an optical phase array, that can be used to sample the beam in different positions, and then we have the problem of recombining all these contributions. In principle, we can do this in the electrical domain. That means we can put an array of photodetectors, and then we need several high-speed electronic channels with transimpedance amplifiers, and we require multiple input electronic DSP running at bit time scale. But actually, turbulence is a slow process in the time scale of a few hundred of Earths, so there is no reason to use a DSP running at tens of gigahertz, and we can use different strategies by replacing the electronic DSP with a programmable photonic processor that is an analog device that can be placed before the photodetector, and so this processor can be updated at the time speed of turbulence. So that's the only hundreds of Earths. So let's start explaining how it works, starting from the very first example of a programmable processor that basically is a 2x1 photonic adder. Optically, this is an interferometer, is a Mach-Zehnder interferometer, 2 optical inputs, and it can be demonstrated that whatever these inputs are, any amplitude and any phase, is always possible by playing on these 2 phase shifters to have the total power at the input that is sum up at one output port with 0 power at the output port. So this is an adaptive combiner. We can use this building block as a basic unit for a multi-stage architecture. So we can build this photonic processor, these trees of Mach-Zehnder interferometer. This can be integrated on a very small footprint photonic integrated circuits. Since we have many phase shifters, so many degrees of freedom, in this example, we have a 16 input, so more than 30 degrees of freedom, we need some electronics. And one of the tasks that we are carrying out in the Focus project EPIC is to care about the assembly, the wire bonding, and the electronics that is required to control these complex photonic integrated circuits. And this is just a picture of the experimental setup that we use. So this is the free space optical beam that is suffer from a scintillation effect. Collimating lenses, we go down into the photonic chip, and then we have a pickup fiber to collect the intensity that has been recovered by this photonic chip. And this is a picture of the setup. This is the free space link. Here in between, we generate intentionally some turbulence in the free space by using a heat gun. And we see that when the processor is off, that means that all the phase shifters are not activated. We have a deep fading, but when we activate dynamically all the phase shifters of this photonic processor, we can increase the average power that is collected at the pickup fiber, and also we are reducing the fading. And these are some results with signals modulated at 10 gigabits per second with the processor that is activated, that is not activated, and we see the change in the statistics of the power and the benefit that is given by the adaptive reconfiguration of the receiver. But with this kind of photonic integrated circuits, we can do much more. This is an activity that goes to the direction of optical MIMO system. The topology is different. Here we have two diagonal rows of Mach Zehnder interferometer, but the concept is pretty similar. So let's consider a first beam with a Gaussian shape that arrives at the input apertures of this circuit. Then is sampled, and by using this diagonal chain of interferometer, we can collect all the power at this output port. Now we assume that we have a second beam that is arriving simultaneously, and this beam is orthogonal. Orthogonal means that it can arrive from a different direction or could be orthogonal in shape. And since this circuit implements a linear operator that is unitary, it preserves orthogonality. So it means that none of the power of this second beam will come out at the first output port. It will go to the second line of this interferometer and can be collected entirely at the second port. So we can separate beams that arrives from different directions with different shapes that are orthogonal in the free space. This is the chip that we use for this experiment, and this is just a result that we achieved. So we have two beams with pretty weird shapes, but they are orthogonal. And since they are orthogonal, what we can do is, even though as they are completely overlapped because of the spatial superposition, with this processor, we can separate them. This is the crosstalk matrix, where we see that we have a very high rejection of the two beams when the system is activated. And this is the eye diagrams of the two channels that are separated all optically by these chips, with almost no penalty in terms of bit array. And another step forward that we are doing is to go in the direction of chip-to-chip communication in the free space. And the nice things of this system, if we have two processors, one is used at the transmitter side and the other is used at the receiver side, optical link, it can be demonstrated mathematically, but then we prove it experimentally, is that this system can automatically find which modes are the best ones. That means it can find the modes that are orthogonal from input to output, so do not have any crosstalk, and they also have the best coupling in terms of power transmission from the input to the output. Mathematically, what this system does is a kind of in situ implementation of singular value decomposition. And this is an example of the experiment that we carried out. So these are the first and the second modes that are established by this between these two chips in the free space when there is nothing in between. And we see that they are orthogonal. Then we intentionally introduce some perturbation. This could be an obstacle, an obstruction, whatever. And we see that if we do nothing, these modes will be no more orthogonal, and the crosstalk is much increased. But we can reconfigure the two chips in order to find a new pair of modes that are still orthogonal. So whatever is the obstacle in between, we can always find orthogonal modes. And these shapes do not belong to any common family of modes of the free space. These are the best modes, the best orthogonal modes to this particular system. And this can be done for arbitrary perturbation. For instance, in this case, we introduce in between intentional phase perturbation by using a spatial light modulator. And we see that by introducing different perturbation, these are different cases of perturbation in between. If there is no active control of the photonic circuits, we introduce a larger crosstalk between the modes. But if in green we see the system is adaptively configured, we always find the two modes that have the maximum power coupling end-to-end, and also the minimum relative crosstalk. Just to give you a few hints of other activities that we are carrying out in the Restart project, this is a collaboration with the University of Trento that is targeting the optimization of the design for the optical phase array to be used in this system in order to obtain the desired specification for the radiation diagram of this array of antennas while minimize the number of elements in the arrays. As I mentioned before, there is a lot of control that is required. So there is a lot of electronics that has to be used for controlling these chips. And here we are using two different approaches. One is to design some specific electronics. For instance, this is an ASIC that can be assembled on the same PCB of the photonic chip and can integrate some electronic front end for the control of the chip. And another strategy is the direct integration of some electronic functionality in the photonic chip. So this is the example of one of the chip that we have recently designed, and this was fabricated in a commercial silicon photonic foundry, where there is the co-integration of some electronic function in the same chip that is used for photonics. And also with this programmable processor, there are many other things that we will do in the Restart project. One is to make the structure a little bit more complex to implement the photonic coprocessor, photonic solvers for mathematical operation, integral, differential equation, and so forth. Very last slide. Inside the Focus project EPIC, we have prepared and we will let circulate a form. This is just a call for expression of interest. That means among the partners of Restart, who is interested in having photonic integrated circuits has the opportunity. Of course, this is an occasion for everybody. We need some information about the needs and what EPIC can be done in this activity. And another initiative that we will do, since we have some chips that are already existing and can be used immediately, the idea is to share these chips, to distribute these chips among the partners in a kind of round-robin exercise, just to share information between our capabilities in the lab to see where we are, and also to plan future run in the Restart project. So that's all. I hope you were able to hear me. I cannot hear you. Is there any question?
The chair is without a microphone now. Okay, we have time for some quick question.
Sorry for the technical issue.
Is there any question from the audience? No, I would ask a couple of questions myself. Do you have any polarization dependence in your PIC?
Okay, this is strongly depends on the platform that you use. In silicon, the answer is yes. So the waveguide and the circuits are almost by definition polarization sensitive, but there are possibility to implement a polarization diversity schemes to make the system polarization independent. Of course, to increase the complexity, but it's just to doubling the structure into and to combine the two polarization. But all the building blocks to implement these polarization diversity schemes are already in the silicon photonic foundries.
Okay, and yes, there is a question from the audience now.
Thank you. It was very interesting. I would like to ask if it's not too early, if there is already some benchmark in terms of quantum interference in respect with traditional electronic circuits. If you are having the idea that there is less quantum interference at small dimension.
I think I didn't catch the question. You mean quantum interference?
Yes, I mean phenomena as quantum tunneling and similar at photonic level.
But related to this free space optics experiment,
Yes.
I cannot see. So we work with, I mean, classical FSO communication. We do not see this kind of effect. We have never tested this this system at quantum application. Okay, but this is something that can be done. But we haven't seen the issue that you're mentioning.
Thank you so much.
Thank you. Thank you. And I have a second question, very quick. Assuming you have not a single wavelength signal, but the WDM signal, do you expect that you would have some wavelength dependence in your peak, or do you think it's almost flat? Or in other words, what you expect is the operating bandwidth?
Yeah, that's a very good question. And so the peak is, let's say, almost wavelength independent. That means that, of course, we have some wavelength dependence. The main constraint at the moment is due to the bandwidth of the grating coupler that we're using for implementing the optical antenna. The bandwidth of the device, as it is larger than the bandwidth of the optical antenna. So it's about 40 nanometers. So this means that it covers the full C-band.
Thank you very much. So let's thank Francesco again. Sorry again for your problem.
No, I apologize. Thank you.
We can move to the next presentation in the session that will be given by Antonio Malacarne from CNIT. And the title is Silicon Photonics for Millimeter Wave Band Signal Generation.
Good afternoon, everybody. We're just waiting for the slides. Okay. Yeah. So I'm Antonio Malacarne from CNIT in Pisa. I'm going to report on our last achievements in terms of using silicon photonics for the generation of millimeter wave band signal. This work is made in collaboration with Ericsson and Sant'Anna School. So, okay, it's coming. So we know that the frequency range from 24 up to 110 gigahertz and beyond is planned to be utilized for communication systems, so 5G wireless technology, also for radar systems. In automotive, the range 77, 81 is already a standard. And then various sub-ranges of the sub-terahertz, like the W band, 75, 110 gigahertz, are already lightly licensed for some applications. In this example is the multi-gigabit wireless and satellite communications. So these about motivations, let's say. Okay, so we want to go high with the frequency, of course, because we want to have a larger fractional bandwidth. So this for radar means a better resolution, and for telecom means higher data rates achievable. Also, this leads to miniaturization of antenna size. And then the drawback is the higher atmospheric attenuation. So here in this figure, you can see about 6G, how the spectrum evolves with the carrier frequency. So we have around 1 gigahertz with a carrier frequency of 90 gigahertz, and then this scales up to more than 10 gigahertz in the sub-terahertz regime. So what we propose are photonics-based technique for the generation of this millimeter wave up to sub-terahertz regime frequencies, offering a solution that is flexible. So we can basically reconfigure the system to generate the frequency we want in this range. It is possible to generate, of course, so since we are taking advantage of the optical domain, we generate the signal in the optical domain, and then we can take advantage of optical fiber links to remotely deliver the signal to, for instance, remote antennas, and then upconvert the signal thanks to photodiode, wideband photodiode at the remote antenna. And then we also came out with the information that this way we are able to provide phase noise performance that are superior to most of the conventional electrical domain solutions. Okay, so okay, so all the features I was mentioning before, bandwidth, antenna size, and the atmospheric attenuation, actually match quite well with the requirements of emerging centralized radio access networks architectures. So where we have a base station, and this base station provide to remote antennas the radio frequency signals, for instance, through optical fiber links. So in a sort of radio over fiber system. So if we want to generate, for instance, a clock in the millimeter wave region, with the electrical solutions, you can use nonlinear media. But then in the end, if you look at the performance, unless the devices are designed for precise frequency generation, so they are customized for a specific frequency, phase noise performance are very far from theoretical predictions, especially if you think about nonlinear media. So basically frequency multipliers. So theoretical predictions tells us that phase noise should scale with the square of the frequency, but then in the end, this is not what happens most of the times. So what do we want to do? We just want to beat two optical modes that are spaced by the frequency we want to generate in a photodiode. Of course, if we use unlocked laser modes, this gives a large phase noise. If we make use of dual wavelength lasers, we get already an improvement, but still a phase noise that, I mean, can be improved further. How? What we commonly use is generation of optical frequency comps. So the modes that are generated, like in a mod lock laser, for instance, they are phase locked, and then we beat two of them or multiple with a specific FSR, free spectral range, so a periodic spectral separation among them in a photodiode in order to get a low phase noise in the RF domain. So even in this case, the system acts as a frequency multiplier. So the system can be this. So we can just take advantage of an electrical optical modulator driven by a reference local oscillator at a lower frequency than the one we want to generate. We induce the nonlinear regime of the modulator, we generate a comb, and then we beat the comb in a photodiode. If we want to make the photodetection more efficient, we can just select the modes that are spaced by the frequency we want to generate. And this can be done through optical filters that can also be integrated on silicon platform. And this is our main goal. We want to realize a device that basically generate either a clock or a signal up converted to the desired RF bandwidth through a silicon photonics chip. There are multiple implementations for the filters, but in case you want to integrate them, there are not a lot of options. One option is to realize break rate instruction in waveguide. So this provides a large out-of-band rejection, and I will show in the next slides how we can get very sharp and very narrow filters. So, okay. So what we use for filtering those optical frequency comb modes are distributed feedback resonator filters. So we basically realize a corrugated waveguide. And so basically each corrugated section acts as a mirror. And then in between the mirrors, we place phase shift elements that then we tune through micro heaters in order to match those elements in the wavelength domain. Okay, so in the end, these structures, without entering into much details, acts this way in spectral domain. So you have a wide stop band region, a few nanometers wide. This is given by the mirror itself, okay, that works in reflection. And then thanks to the discontinuities we introduce along the structure, the distributed structure, we realize this passband behavior. And then if we make multiple cavities, we can improve the steepness and the shape features of this filter. Okay, so this is the way we realize a passband filter in the optical domain that is going to be down to a few gigahertz wide. So this is the structure. Yeah, we realized on a silicon platform for this is a single filter based implementation. So we inject a laser on one arm, the upper one, we modulate in order to create the comb. We select a combo mode through the optical filter, and then we combine back this mode with the original laser mode. This way, we obtain our frequency multiplication with respect to injected frequency to the phase modulator. So in this case, 18.5 gigahertz multiplied by a factor n at the output, given that we have a photodiode with a bandwidth that supports the frequency we want to generate. So this is the implemented PIC, so photonic integrated circuit. Okay, you can see some structure, the FBR, the long phase modulator. Then we couple optical inputs and outputs through a grating coupler array coupled with a fiber array. And then we have DC pads for control of the circuit and NRF GSG input pads for the modulator. So yeah, this is a setup we used for measuring the phase noise we get at the output of the scheme once we have this higher frequency oscillation after photodetection. So this slide is again about the filters, because actually, so this waveguide structure has micro heaters for finely tuning each phase section. And then there is a long top metal heater for shifting the whole spectral response in the wavelength domain. So there is a fine tuning mechanism and a coarse tuning mechanism, still thermal based. So there are, again, always thermal shifters. And you can see some examples where we demonstrated the fine tuning in the top, and then the long thermal heater in the bottom example there. And a few features. We got a passband filter loss of 1 to 2 dB, depends on the realization on the employed foundries. The design can be 3-4 heaters, so those are just ranges, 1 to 2 dB, 1 dB band from 4 to 10 dB, 10 gigahertz, and the rejection at 10 gigahertz larger than 40 dB, a stop band that also is the tunability range of the filter from 5 to 6 nanometers. And then it's also indicated the efficiency of the thermal tuners. So in this example, this experiment, we achieved the black comb, and then we filtered different harmonics, coupling them with the original laser in order to generate different frequencies. But of course, if you can tune the input frequency, you can get a variety of frequencies at the output. So this is just an example where we demonstrated ×2, 3, 4, 5 with respect to the local oscillator frequency. Those are the filter responses once we tune for getting ×2, 3, 4, 5. With the indicated average power consumption per heater. So you have to multiply by 4 if you want to know the total power consumption. And then we made phase error in phase noise performance measurement. So this is the reference, and those curves are the different achieved frequencies. We came into this additional term that was given by the noise of the employed DC sources driving the peak. Indeed, when we tune the filter, this term scales with the dissipated power. But if we just tune the laser and we keep the filter with a specific dissipation power, this term is constant. So we just add low-pass filters to remove the term and get these final results. So if you can notice the dB carrier per hertz difference between the reference and the other terms, it comes out that it's very, very close to ideal phase multiplication, and this is confirmed by the time jitter versus multiplication factor. That it's very close to the ideal one, that is the red, and that was also obtained by external wave shapers, filtering by external wave shapers that do not introduce any spectral fluctuation. That basically comes from temperature accuracy, temperature stability of the device, because those filters, of course, are temperature sensitive. This is the package device. So we performed the RF wedge bonding to the phase modulator input. Then we glued a fiber array. And we also designed a PCB for matching the impedance in a range 18-25 gigahertz. In the simulation for designing the PCB, we also took into account the wedge bond inductance. So we included that in the simulation, because in the design, and this is quite an important point. And those are the simulations and how the device is robust to inductance variations and also impedance variations of the PN junction of the phase modulator. And those are plots coming from the experimental characterization of the packaging. So this is the filter, the comb generation, and then the S parameters. So quite well confirming the design. Probably we can do better, but this is also related to the fabrication process of the PCB. We experienced some extra etching, over etching, so we can do better than this, but it's already something not too bad. So we used this device for generating this 98 gigahertz optical clock. You can see in black the spectrum at the output of the device, with phase noise performance again, and time jitter that is practically the same as the local oscillator at around 20 gigahertz. So in this case, is a time five multiplication factor from 20 to 100 gigahertz. And we used this optical clock in a wireless communication transmission. So we basically we generated this clock in the optical domain, then through a Mach-Zehnder modulator and a photodiode, we imposed a data signal, and then we up-converted the data signal to 93 gigahertz with an intermediate frequency of the signal of 5 gigahertz. And then we transmitted on a 2-meter wireless link, and we tested the error vector magnitude performance at the receiver. So we were able to generate up to 4 gigabit per second QPSK, 2 gigabit per second 16QAM, and we are currently working on doing the same with OFDM signals. That is actually our main scope, and this is given by the interest that Ericsson has on this approach, especially for the phase noise performance that for OFDM transmission are particularly important. So next steps for the millimeter wave band signal generation are the use of structures based on 2 optical filters. so as we can improve the spectral efficiency. We can filter optical modes from one side and the other side of the comb in order to get higher frequencies. With an unpackaged device, we already achieved the 200 gigahertz generation. Then we also designed a dual resonant DFBR filter, so able to filter two modes of the comb. So of course, in that case, it's not a flexible device because it's designed for a specific frequency. And then we are also investigating the use of optoelectronic oscillators still, where the memory element and filter element is again our DFBR filter. And then of course, thinking about the two-arm architecture, in the arm where we just passed through with the laser, if we place an IQ modulator, we can also get a single sideband carrier suppression modulation. Then coupling with the selected mode, you can directly up-convert the signal at the photodiode output. And this is another approach. And then,
can you go quickly to the conclusion, because you're
okay, so just saying that we have an open point that is the automatic tuning of the filter, because of course tuning the filter to go from that condition to this one, we can do that in lab, just looking at the spectrum, but we are looking for automatic solutions to do that. And so this is an open point. Thank you.
Any question from the audience?
I have a question, if I can.
Yeah, sure.
Okay. Yeah, regarding the tuning of the filter, when you shift the passband by playing on the common heater, do you have to refine a bit the tuning of the local ones or not?
So the exact answer is yes. So the strategy we use in lab, we refine the shape of the filter. Once it is optimized, we tune with the long heater. Once you do that, a little adjustment on a couple of heaters over the four, it may be necessary. Yeah, if you really want to optimize it to make it as flat as possible, and this also, since the shape of the filter can affect the phase noise performance, yeah, sometimes you need to do that. And then the package is already quite well optimized for temperature management. It includes a tech, a thermistor that is integrated. We are able currently to achieve an accuracy of plus minus 0.001 degrees. So, I mean, it's...
Yeah. Sorry, and in the insertion loss of the filter is the same across the tuning range, or it changed a bit?
The width, you mean?
No, the insertion loss. The insertion loss.
The loss is quite uniform. It is the band that changes a little bit. The best condition is centered, is the narrowest one. But the loss, I would say that it can be a variation of 1 dB in the whole range.
Okay, thank you.
So let's thank the speaker again.
Thank you.
Okay. We move to the talk by Mehmed Ibrahimi, Politecnico of Milano. Uncertainty aware QoT forecasting with machine learning and avoiding QoT degradation through EDFA Raman amplifier upgrade in CL band networks.
Hi, everyone. My name is Mamade. I am with Politecnico di Milano. Basically, the talk today is more about showing the activities that we've been involved with as a group. I work with Massimo Tornatore. The outline of the talk is focused on showing first the work package that we are leading, the one which is named AI-aided automation, multi-layer control and acceleration for optical networks. Then I'll go a bit into the technical contributions, more showing what we are doing and why we are solving it, and less maybe on how, and also showing some ongoing works that we're doing. So to get started with the VP5, with the work package that we're leading, this is a high-level architecture showing the main building blocks. The idea here is to show that optical networks have different segments, meaning that there's the access part, the metro, and the core. The idea is that there will be an SDN controller for each of the separate pieces of the network. And then there's an orchestrator, which contains the various modules, various algorithms that we are developing in order to optimize and to make sure that the network is operating as we want to. In specific, I'm going to be focusing on two main things, on QoT forecasting, and also I'll talk a bit on failure detection. Before jumping into the more technical discussion, first I want to just make a point on the challenges that we've foreseen and the challenges that we're facing. Basically, we've identified three challenges. The first two are the continuous monitoring of the light path quality of transmission, and when going to the context of multiband transmission, what happens there? What are the peculiarities? In particular, talking about the continuous monitoring, we focus on capturing the random fluctuations in the SNR, and to tackle this problem, we have developed some QoT forecasting frameworks, and when dealing with lag from real data networks, then we've developed some transfer learning tools. As ongoing works that I'll talk about in the last slide of the presentation, we focus a bit on disaggregated optical networks. For purposes of keeping it short, I'll focus more on these parts. So the first contribution refers to the uncertainty-aware QoT forecasting. So the questions is, why do you want to do QoT forecasting? Here is a capture of a real network by Microsoft in 2015, where you see the fluctuations on the signal-to-noise ratio of a light path. So the idea is that we need to have robustness in the face of uncertainty, since the fluctuations can be 1 dB or even more. And the question that we've posed is that, can we accurately forecast the fluctuations of the SNR while still maintaining significant statistical guarantees? So to somehow lay out the problem, the idea is that based on the historical data, you want to learn what's going to happen in the future. In this case, this snapshot shows a scenario in which, for up to a moment t, you are learning from the fluctuations of the signal, and the idea is that you want to predict what is going to happen from a moment t+1 up to a given moment h. The contributions of this work are two. First, we want to accurately perform QoT forecasting while exploiting the correlations between different light paths. Then, on top of this, we also want to provide robustness. Robustness because if you see on the shaded part, we don't only want to predict what is going to happen in the future, we also want to provide confidence intervals in order to determine if the prediction falls within those confidence intervals. So without wanting to bother you maybe too much with the architecture, the idea is that we are using a classical encoder-decoder architecture with multiple LSTM layers. What is important to see maybe from this architecture is that there's time series of various light paths that come as input, and there's multiple LSTM layers that serve to predict what is going to happen up to a moment of t plus h. As you see, what is important to see here is that the output of a moment t+1 is used as an input to the LSTM decoder in a moment t+2. To evaluate the tool that we've developed, we've used a Microsoft data set, which is available online. We've considered two scenarios. First one is considering that the channels are all in the single length, and scenario B is considering that the channels are from different lengths, because we want to see how the correlation between different light paths helps us make such estimation. As baseline, we use a state-of-the-art MLP-based forecaster. To just show some numbers, here we see the comparison of our approach with a state-of-the-art approach in terms of mean square error and mean average percentage error. We see that for scenario A, we outperform our approach, outperforms the state-of-the-art. And the same thing happens also in scenario B. Of course, comparing scenario A and B, you see that the value of MSC and MAPE are much higher because you are considering light paths from different lengths. And without wanting to bore you maybe too much, I'll try to focus on two illustrative examples. Here we see that in the time that we consider as historic, we see a fluctuation of the values of SNR. So the prediction that we provide ensures that the grand truth falls within the confidence intervals that are defined. Of course, this is let's say, a desirable scenario. However, it might be the case that because in the past there have not been many fluctuations, in the future at a certain given moment, the value of the SNR either increases significantly or drops. And from an operator's point of view, this can mean that you basically have an alarm which tells you that there's some strange behavior in your system. What is important, and I think falls well within the mission 7 of Restart, is that we want to help the community to also work together. So we have made the code public, and the idea is to use this as a means to also collaborate with people that are interested in doing more or less the same works. Another contribution is one which is related to failure detection. I'll go very briefly because I don't have much time. So in optical networks, we know that there may be hard failures when things such as fiber cuts happen. What we care about is soft failures, which are reflected in the fluctuations of the QAT of light paths. And such failure, soft failure management scenarios can mean with dealing with a case when we want to detect if there is such a failure. So we want to know, based on some measurement of the optical signal to noise ratio at the receiver, whether there is a failure or not. And doing so, we are actually able to prevent service disruption. Another scenario is localization. Besides knowing if there is a failure, also determining where does the failure happen. And this, at the end of the day, is important because it allows to reduce the mean time to repair. Why do we use approaches such as transfer learning? Basically because there's not sufficient data from real networks, or acquiring data is very costly. So using approaches such as transfer learning helps us somehow tackle this problem. So the idea is that you have an optical line system, you have measurements at the receiver, and then you do machine learning classification in the case of failure detection as a binary classification or multi-class classification in case of localization. I'll just go quickly. Okay, so the analysis that we did was done on some data that we got from NICT in Japan. Here we considered 3 scenarios in which there's an additional attenuation in various links, and we considered different light paths. The question that we posed is that, is it possible to transfer the knowledge from one type of failure to another. So is it possible to learn from localization to detection and vice versa? And just to maybe give some numbers, here the plots show a scenario of the transfer or the accuracy on the data set, on the target data set, and the number of data samples which are added. What is important is that in case, since neural networks are usually used in the context of transfer learning, it is necessary to retrain layers of the neural network in order to get the desired output. At the end of the day, what we've learned from this is that it is possible to learn from one type of failure or one type of sub-failure detection to localization and vice versa. And to conclude the talk, this is a work that we've been doing, which is part of VP4, which is led by Politecnico Torino. Here, the idea is that since this highway of optical networks provides abundant bandwidth, at the end of the day, is not that abundant, and you can try to explore new methods to use more and to have more bandwidth. The idea is to extend the transmission spectrum beyond the C-band. For example, use the L-band or the S-band and so on. Of course, there's no free lunch. So as a result of this, what you get is that the signal-to-noise ratio of the light bus is degraded. So what can you do? One possible solution is to introduce hybrid amplification, which introduces EDFAs and RAM. What does it mean to introduce hybrid EDFA? It means that in the locations where you have an amplifier, which is in the C-band, you introduce an amplifier in the L-band, you introduce additional devices such as splitters and couplers. If you add also Raman amplification, then of course, you introduce the Raman pump as well. At the end of the day, why does this matter? It matters because here is an example of an 80-kilometer fiber. The SNR of a light path on the C-band is around 26. When you extend the transmission from C to L, then the SNR of the light path drops. Keep in mind that this is a specific case of 80 kilometers. So in a scenario of a whole network, of course, the impact is more significant. So what we do is that we introduce hybrid amplification to ensure that the SNR is improved. So why not do it everywhere? If it's so obvious that you increase the SNR, I mean, you cannot do it everywhere because it's costly. And in fact, what we try to do is that we try to compare some optimized approaches against some baseline that considers introducing Raman amplification everywhere. We did some analysis on various continental and national topologies with various considerations on the traffic as well. Long story short, we show that if you optimize deployment of hybrid amplification, of the placement of hybrid amplification, you can achieve up to 50% savings compared to the baselines that I mentioned before. Just to make a point that this work was just recently published, actually 2 days ago. So if you are curious to learn more, you can check out the paper. So to make sure that I remain in time, I want to make a point on some ongoing works that we've been doing. I want to relate to what was said yesterday during the discussion of Mission 3 of Restart about innovation. So the idea here is that we consider that the access, metro, and core networks are often managed by different entities. And such entities are not always willing to transparently share the data that they have, the machine learning models that they develop for problems such as failure detection. So at the end of the day, the idea is to develop some privacy preserving federated learning to ensure that you can still keep the privacy and the communication between various managers, let's say, of different parts of the network. Of course, doing so is crucial to also receive or retrieve optical parameters through digital twins, such as the one that Professor Kuri will be talking in the next talk. And yeah, that concludes my talk. Thank you very much for your attention.
So thank you. Is there time for one quick question? Yes, Vittorio, can you please come back down the microphone?
A quick question about RAM amplification. So you consider a specific configuration, how many pumps and so on, or just a generic idea of Raman placement?
So the idea is that we consider that we introduce a Raman pump, which is able to compensate for 60% of the losses in backpropagation. It's a very generic. Yeah. No, I mean the analysis is not done in the context of physical layer, which I assume what you're referring to is more on introducing algorithms and methods and proving if they're able to ensure improvement in the SNR, because at the end of the day, the SNR calculations and the feasibility of light pass is done in an accurate way. Yeah. Yes, please. And yeah, and we're very open also to collaborating and introducing the 5 pumps. Thank you.
So thank you again. Thank you again. And I think, Vittorio, you can stay there because you are the next speaker. And final talk is challenges and benefits of digital twins in optical fiber networks.
Sì, okay, thank you to everyone. Thank you for the invitation. My warm apologies for not choosing the proper template. I'm sorry, someone. It was much easier to use my template. Okay, so let's talk about the digital twin that, you know, everyone talk about digital twin in the last couple of years. I listened to digital twin about everything. So let's focus on the optical transport layer in the optical network. And let's start from the beginning, because I listen many times to talk about the digital twin, but rarely I heard someone defining what the digital twin is. And in my opinion, sometimes it's used not in the proper way. So if you look at the past, who proposed the digital twin concept was the NASA, not the last of the institution that defined the digital twin for applied object, but that is written here. But if you can expand the concept of digital twin, is a high fidelity model of the system under and the environment impact, which can be used to emulate the real twin. So the digital twin is a framework that is able to emulate the behavior of the system. Thank you. Of the system and the effect of the environment of the system. And in this way, the digital twin may be exploited to optimally control the system that you want to control. This is the generic definition. That is not mine. I repeated something from NASA. And if you look inside the digital twin, there is made by 3 big elements. Sorry, there has been some issue in the font. So the core is the model that is able to emulate the behavior of the system, but is as important as the model core of the digital twin are the two interfaces, the one from the environment that feed properly the model, and the other is the output of the digital twin that is able to control the system. These three elements are fundamental to define something a digital twin. So move on, and specifically on the optical network, on the transport layer optical network. So the model is very well defined, is a weighted graph that move on. They take into account of the transport on effect given by each network element. And this has been dramatically simplified by the introduction 13 years ago of the dual polarization coherent technology that has transformed the optical transport that with intensity modulation was something just for gurus in a over simple scenario. But still, the main issue that is in this context is the definition of the interfaces. Here I list some keywords, some buzzwords that are around in the world, but still we are working. And it's not an issue that is a technical issue, it's a political issue mainly. And of course, machine learning, artificial intelligence in general may help in retrieving this data from the field. But for sure, we need to define, and are under definition by several different institutions, these interfaces. Let's move on. So why the physical layer in optical network is so simple? Because it has been extensively shown that the effect of the propagation and dual polarization coherent technology on every transparent light path is very well given by a unique parameter that is commonly called generalized SNR. It's actually the SNR. In the last 10 years, we have used several different names. I would prefer to use SNR, but generalized SNR is typically the mostly commonly used definition that include at the numerator the power the received channel, and at the denominator the overall amount of noise introduced by propagation that are mainly given by three sources. One is the AEC noise introduced by the amplifier. The other is the nonlinear interference or nonlinear interference noise that is introduced by nonlinear fiber propagation, is a nonlinear crosstalk. And then we have the linear crosstalk that happens in ROADM in switches. All are very well modeled as Gaussian disturbance. And so is an additive white and Gaussian noise channel. It's an excellent approximation. And then we have also to consider the noise introduced by the transmitter and the receiver. The gain are very well. So the transmitter is the AEC noise typically. The receiver is introduced mainly by photodetector, but the model on the decision signal is Gaussian. At least for propagation on chromatic dispersion exceeding 2 picoseconds nanometer per kilometer. If you go close to the zero dispersion, so you will see some surprises, but most of the scenarios also in multi-band down to the E-band or up to the E-band, depending if you look at the frequency or wavelength, is satisfied. Also in the O-band, you can get good propagation of signals. Okay, and then the transmitter, the transceiver that put the data on each light path, that the transceiver have a good model, yes, is the one you read on the optical communication book. The behavior, if you take the prefect BR from the transceiver, you characterize versus the OSNR in back-to-back, and you get a behavior like the one. This is a qualitative behavior, of course, but you always see something like this. And so a simple model, you can get a simple model just based on threshold on the OSNR that is defined by the maximum tolerable BRR by introduced by the coding, and then you read on the y-axis the threshold. So the simplest model is this one. And then you can also use a semi-analytical model that that is the one that take advantage of the formulas that you read on every book for QPSK 1/2 complementary function of the GSNR divided by 2, square root of the GSNR divided by 2. For the other modulation format, it's the same. So in general, you can have something like this, where you have the BR that is given by this. And of course, you need to consider both the propagation GSNR and the transceiver GSNR can be can be characterized in back-to-back. So this is something that is kind of easy. Typically, vendors don't want to expose this data, but you can get characterization from a simple lab setup. And the additional penalty, as it happens in every additive white and Gaussian channel, you can take into account in a very good way the additional penalty mainly given by PDL and filtering penalty and chromatic dispersion and DGD from PMD if the chromatic dispersion exceeds a certain maximum value depending on the implementation of the receiver. They introduce a penalty that shift on the right the back-to-back characterization and becomes more demanding in terms of GSNR over simple. So, and going into details in every network element, identifying what what we have to take into account. The fiber is very well approximated by an element introducing the NLI, that is identity Gaussian noise. And then, of course, you have to consider, mainly when you go to multiband, the frequency variation of the loss, the stimulating element scattering, the frequency variation of the chromatic dispersion, the frequency variation of the effective area, because the effective area in the C band is 80, in the O band is 25. But given this, everything is good. Which are the issue in modeling? The modeling, there are the main issue is the lumped losses. As I mentioned before with the colleague from University of Padua, you have lumped losses. So if you do simulation, you do, okay, my fiber is uniform. It's going from here to here, 50 kilometers, 80 kilometers. The loss is this one. If you look at the real fiber, you see some jump given by, if you read the OTDR, you will see lumped losses and so on. See, these are the degree of uncertainty that you have to consider. Here is the door open to the artificial intelligence to fill the gap. Optical amplifier, practically is a super simple model. Is something that introduces some gain and some noise, full stop. But and so if you know what is the gain and what is the noise, it's really simple to be taken into account. But if you look at the real scenario, the EDFA are strange guys because of the erbium that gives some strange behavior. If you put Raman, you will see some surprises and so on. And so if you are able to get gain and noise figure, everything is very good, but you need to acquire from something the gain and noise figure. And the first issue is that there is no common model so far. After more than 20 years that the DFA is mature device, there is no common model. OpenRODAM is trying to propose an open model now in 2023. The first open model. You cannot find any amplifier with an open model. This is the big issue. But if you overcome this, for sure, machine learning can give excellent models of the amplifier. So, RODAMs are really interesting devices. The one based on LCOS are really fascinating from an engineering point of view, but they introduce something, and specifically they can introduce some AC noise if they have some SOA internally, cross-stall for sure, filtering, and PDL. So let's go into details. What is the PDL? The PDL penalty is not a solved problem, not yet. Professor Macozzi proposed a solution for the intensity modulation, but for the coherent vaporization scenario is completely different, and we are developing a model. And to talk to you, I never able to pronounce your name, but I will learn some point. And then the PDL effect is one of the main responsible, the fluctuation in time of the GSNR, because it depends on the rotation introduced by each fiber span that depends on mechanical stresses, temperature variation, and so on. You observe in VR fluctuation that follow the temperature variation in time, and if it's in underground in a metropolitan scenario, we'll see the effect of traffic. Okay, but in general, the GSNR, due to the PDL, has a Gaussian distribution, truncated, but we have several Rodan crosses, and the challenge that we are really close to get the final result is to define this GSNR distribution in order to take into account properly what is the impact of the PDL. Filtering penalty crosstalk still are open issues in order to get a good model, because okay, crosstalk is simple, but you need a characterization. And filtering is again simple, but is also you need characterization of filters, and also you have some statistical effect depending on the environment. To give a proper model is a challenge, and probably also in this case, machine learning may help in assisting the deterministic digital twin. And then you have additional metrics that are kind of simple. The accumulated chromatic dispersion, the accumulated latency, because I want to remark that a fiber, 1 kilometer of fiber introduce 5 microseconds of latency is not negligible, the latency introduced by the fiber, and the PMD. There is a model, yes, there is a model that is commonly, we have extensively tested this model that is GMPY, that is an open source project, works perfectly. So you can have a look at the several papers where we propose our test in the green field and also brown field thanks to Microsoft. The issue is, again, in getting data from the environment and operating the control. The effect, if you have a digital twin, is a partially distributed optical network where you can perform the full control of the network in a disaggregated way where you control the line. And within the multi-layer hierarchical controller, you have an open optical network controller where you compute path computation, and you can also add the monitor agent that will come on later. The yellow part is the challenge. Are the protocols and telemetry and all this data that are not well defined. We are building in our lab, we have already done a demonstration, and we are executing this direction within the Rigoletto project, and you can find in this paper on IEEE Transaction Network Management Service the first demonstration that it is feasible. Then let's go in details on each element in this picture. The LiPath computation engine is kind of simple. You get the data from, if you get the data from the physical layer, you compute the GSNR, and you have a look at the model of the transceiver, and you deploy the maximum bit rate on the LiPath, also deploying some margin. Which obstacles? Open protocols, open models. The same for the optical light controller. We have extensively shown this also the last NDM. We have done an interesting presentation on this, that the line can be controlled, and the target is quite simple, is posted there. These are the formula, but again is which are the obstacles to get open protocols, open model, for a full knowledge of what you have in the field. And then last but not least are the monitor agents that are a generalization of the sensing. So in the field, you have plenty of information about what's going on. And so if in an open environment, you can put a monitor agent that exploiting artificial intelligence, machine learning, and the physical layer digital twin, reading the telemetry, can detect and localize the failure, can predict incoming failure, perform in general what I like to call the physical layer tomography, that is able to have a look at what you actually have in the field. And also the other side of the same object is to perform environmental sensing, starting from earthquake, as Professor Boffi presented at the very beginning, environmental sensing, earthquake, traffic, and all the other activities. So, comment and conclusion. From a theoretical point of view, and not also from a practical point of view, we have extensively proved that thanks to the GMPY project, that the physical layer digital twin can be profitably exploited. And you can control a network, a multi-vendor network in a partially disaggregated way, in an effective way. Of course, you need a system from machine learning, artificial intelligence to feed properly. This is the core of this digital twin, that is the model. And in red, I wrote what is the missing part, that are open models and protocols. But a lot is moving on in Open RODAM, in OAF, IETF, Telecom Infra Project, and IEEE, and I don't know, I forgot some institution toward the openness. And so, if I may predict, we will see some degree of progressive openness in the physical layer of optical network. That last comment, the optical network are everywhere, and with 5G and 6G will be more and more wireline with respect to cable generation. So the fiber goes to each antenna, and the wireless segment is just few hundred of meters. All the other part of the overall internet is based on fiber. Every year, billions of kilometers of fiber are installed worldwide.
Thank you very much, Vittorio, for the inspiring talk. Questions from the audience? No questions? Okay, I can start asking one question to you. You know that coherent detection system based on DSP can provide you some information about the accumulated dispersion, the PMD, the optical signal to noise ratio, and so on. The point is, to you, this information, it can be accessible. I mean, the operators are willing to share this information, or there is any model that allows the operator to share this information without compromising the, let's say,
there are some
critical points.
Is the how to say, the privacy issue is the big issue, and operator don't give you any data, no way to get data that are really precious. That there is this database from Microsoft, but for sure this is the really precious set of data. Also on the geographical footprint, if you share this data, you can operate on this. What is it is something that is becoming, beside the control plan and data plan, a new plan as we progressively introduce, that is the telemetric plan, and that includes all these big data that is there, that are there, and are really precious for the community, for the network, for many different data. So we have billions of kilometers of this glass World Wide Web that, besides carrying all the data for the impact, if you look at the statistics, is 99 point something. So satellite is carrying just a small portion. Everything is carried by the optical network, and also may help a lot in in sensing what happens, but also in giving the maximum capacity, reducing the cost, and so on. This is something that let's see what will happen.
Thank you.
You're welcome.
Any other question? Okay, so let's thank Vittorio and the other speakers again.
Tra gli ultimi ci sarà io.
Okay, so sorry to be the bad guy, but there is no coffee break now. So we'll start right away with the next session so we can finish on time. So the next session and last session is application domains and cross topics. I'm Michele Zorzi from the University of Padova. I'm chairing the session. So first speaker is Ana Cabrera Tobar from the Politecnico di Milano. I think we are ready to start. So I ask you to please either be silent or step out so that we can start and the speaker can deliver her talk.
Good afternoon. So, yeah, thank you. There, now, okay. Good afternoon. Right now, let's put a little bit of energy right now. So now I'm going to talk about energy resilience for telecommunication networks. And this is part of the focus project SPOC 3, Renewables for Resilience. So the outline of this presentation will be first the introduction, talking about some policies for resilience, strategies, energy management, challenges, and conclusions. So the focus of this project, it will be to build energy resilient systems in the way that it should be sustainable, green, with reduced cost, and also efficient. The objectives of the project is that we should design a power supply that it should be resilient, also the smart energy management, and also demand response for efficiency, reduction of cost, and operation in normal conditions, but also during natural disasters. And finally, a failure detection management. The possible collaborations that we could build is with the SPOC 7, SPOC 3, and the SPOC 5. And the scenarios that we are going to be working on is, first of all, business as usual, disaster management, and rural areas. And the indicators will be specifically on efficiency, resilience, and emissions. So first of all, when we have a natural disaster, for instance, right now, if we have earthquake, what you will do, what it will be your decision. So in that way, we are thinking how we are going to answer in this moment if we are in the house, if we are in the building. So the same performance, we have to think in a bigger scale. So let's see what is saying the data. Right now, the data is saying that the majority of the failures on telecommunication is because of human errors rather than power outages. What is the human error talking? We are having 91% of user loss hours because a wrong update or there is a problem with the maintenance of the equipment. However, if we talk about power outages, we can have problems because of natural phenomena, hardware failure, and also the human error. But this data could increase in the following years because of natural disasters. So we have seen the data, what is happening with the natural disasters, natural hazards, like earthquakes, like floods, like landslide, hurricanes, what is happening with the power outages and the telecommunication network, and also how we come back to the system, the outage time. We can have weeks to months, or also depending on the natural hazard, just minutes, hours, days. So we have to plan for those type of problems. There is a well-documented case about the Hurricane Katrina and what is happening with the telecommunication network and also the power supply. So we can see on those pictures that we have some problems on the batteries because of the flood, but also because of the wind. Also, we have lost some transformers and some lines of the power supply. So this is a very well documented, but we have to think in other cases and scenarios and how we are documenting as well. For instance, there is this case that we just lived about Emilia-Romagna, but we don't have the data what really happened with the telecommunication network, with the power supply, and we need that in order to give a better response on the power supply. What happened is that in order to restore the service, they sent 900 people, 70 vans and 20 vehicles equipped with radio stations and mobile stations. But in order to supply energy to those mobile stations, they use electric diesel generators, and also depending where it was located, the problem, they had to mobilize helicopters. And sadly, because of the climate change, we will have more of these problems in the future. Italy will be more affected with flood, but also with heat waves. So because of this, the policies about resilience is changing. Usually, we are talking about of having a backup power for remote site of 8 hours. And for urban sites, 4 hours. But now they are talking to increase this number to 72 hours of backup power supply. So in order to give this power backup, let's understand a little bit how the power system works. First of all, we have the generation, transmission, and distribution. In the side of the distribution is what we have, the telecommunication, the base station. And usually this one is isolated from other loads. For instance, if you have a problem in your house, you did something wrong, that shouldn't affect to the base station that is next to it. And in order to give some solutions, we can provide some power supply in a way of a nanogrid, microgrid, or a virtual power plant. Nanogrid is a small system with a small power supply like photovoltaic, wind power, or also it could be also diesel generator, but we want to be zero emissions. Then the microgrid is a bigger scale of the nanogrid, but if we want to manage all of that, the concept that we usually talk on power system is virtual power plant that we enter to the electrical market. And if we are talking about base stations, we can have the base station normally is connected to the grid, but we can give some solutions in order that it can be resilient, but also green, with the inclusion of renewable energy like photovoltaics, but also some batteries, but also it can be off grid that is only connected to systems that it will last all day working the operation. But in order to have all day working, we need some batteries, fuel cells, also UPS. It could be, and right now, usually base stations use diesel generators. And in a moment of natural disaster, we can have mobile backup systems. An off-grid microgrid example we see on this picture, this is in Norway, And this is has a equipment of fuel cells, photovoltaic panels, and wind turbines. And the idea is that this is not connected to the grid and is resilient all year long. But in the case of natural disaster, we have to move the energy and we have to plan it as well. For instance, when there is these problems that we know that a natural disaster is coming, we have to put a diesel generator or a portable energy beforehand in the area that we know that a problem will happen. So usually we are using portable diesel generator, but now there is also these other solutions that is with portable energy storage and portable fuel cells, and also portable nanogrids. However, when you are talking about a natural disaster, you have to think how you are going to move all of that. So also logistically speaking, you have to see what should be the easier way to answer. But also we have to think, where are we building the base station? So now, because of the climate change, we are having a problem that some of the natural hazard that wasn't happening in an area now is happening in another side of the country. So because of this, we have to rethink our planning. And we have to see what is happening with the power supply for that base station, where we have to put it. If it is a flood, if an area for floods, then we have to move this, the generator, the battery, we have to build it in another way. So now let's see the energy management. We want to build an energy management that is efficient, reliable, sustainable, and zero emissions, but also that works during natural disaster. So usually the energy management, we want to optimize the renewable sources, the battery, but also to control the demand, to reduce maybe the consumption of the base station by different techniques that all of you know. But in the case of a natural disaster, we have to play with all of that. We have to optimize which type of data we want to send, but also which type of energy we want to use. And in order, we have to make it in a way that we don't consume all the power that we are having in our diesel generator or the photovoltaic system or the fuel cell. So during emergency, we have to prioritize critical loads, reduce power consumption. We have to give a solution between demand response and optimal energy management, and of course, cooperate between the different systems, power system, telecommunication operators, in order to share resources and logistics, especially during emergencies. So as you can see, many challenges can come from this. First of all, to build a system that is sustainable. For instance, one problem that happens, well, I'm coming from a country that we always have natural disasters. So we are used to have them. So when we have earthquakes, we know that the hospital has its backup system. What usually happens? They have forgotten to put the diesel. And then the backup system doesn't work. So now let's see here what is happening, or what has happened when floods came to Italy. When this type of natural disasters is happening, why the power system didn't work? Why the telecommunication didn't work? Somebody forgot to refill the diesel generator, or they put it in a bad place. What happened with the battery? If you are having shortages of 40 minutes or 10 minutes of power, that the base station should be able to overcome, because it's a critical load. But if not, something else is happening. We have to see all of this and to have the data in order to analyze effectively what is happening. So another challenge is to find the optimal locations of sources, but also to build the base station, to analyze the risk of the area. Now that we know that this is changing, we have to analyze all of this in order to see how to respond during emergency, power system and telecommunication. Then we have to plan according to the climate change that is now happening. So some of the conclusions is, first of all, we want to build a system that is resilient, especially during natural disasters, using renewable energy, new technology, but also we need some data in order to provide a better solution. What is happening in the country and in Europe? In order to build this reliable power system, also we depend on maintenance, also on an optimal energy management, but it has to be together between telecommunication and energy. So thank you so much. And if you have some questions.
Thank you, Anna. Are there any questions from the audience? Yes, Antonio.
Yeah. So the idea also, we are thinking.
Can you repeat the question briefly so that the people online can hear it? Thank you.
So he's asking about how to solve this problem, not only to answer during the disaster, but also to plan beforehand. So to build the system reliable enough. And also we are thinking on that because when you are building for resilience, you have to be prepared and then in the moment act and then after. So it's the 3 steps. So if you design reliable enough, it shouldn't be a problem, but always there is a problem. Always, at least in engineering, we know that we have to think in the worst case scenario. So during the problem, what could be the solutions as well? So it's the two ways, they go together.
Okay, any other questions? So one thing, there is a correlation in some disaster scenarios between losing power and compromising the actual telecommunication infrastructure. So you lose your power supply, but maybe you cut the line from the base station to the network. So is there any, and you focus only on the first part, right? But is there any joint strategy to recover power and providing connectivity when it's missing? Or do you see these as 2 independent problems that need to be addressed separately?
Half and half.
Okay.
So first of all, in the moment of a disaster, you need the 2 things, communication and power. But if the power, it takes longer to recover, then you also have the telecommunication, also the moving telecommunication system, and that could help. And that's why also those moving recovering system should be also with power supply that also should move. So I think it's a joint solution, but at the same time can be independent in order to be reliable.
All right, then thank you very much, Anna.
Yeah.
So our next speaker is Giovanni Perin from the University of Padova, talking about topics within the same project, actually, which is a focused project, R4R. addressing distributed optimization in networks with federated learning.
Okay, so thank you, Michele, for your kind introduction. As he said, my talk will be about distributed optimization. So who likes math? Nobody, very well. So I guess this was an engineering meeting. And I will try to make my best to make you interested in what I say. So first of all, why this falls within the scope of R4R? Well, like Anna said previously, R4R is about energy management, and specifically, I work within the work package 2, which is named Machine Learning-Based Resource and Energy Management. So we have 2 ingredients. The first one is machine learning, and the second one is energy management. Who does work with machine learning? Everyone, even though nobody is raising their hand. And of course, also energy management is a hot topic. You know about the climate is changing. And in particularly in these days in Bari, it's a very hot topic. So we have machine learning. And as the title suggests, machine learning must help to optimize our energy management. But this is just half of the story, because machine learning is energy hungry. So we also want the arrow back, energy management that makes efficient machine learning, so that we gives rise to this positive loop. And we like positive loops, unless you are control engineers. They don't like positive loops. Well, anyway, what I'm talking about in this talk is federated learning. It's freezed, okay. So federated learning, we already had a couple of talks about federated learning. Very briefly, the objective of federated learning is that of learning, of minimizing a loss function, which is global, by doing it in a distributed way across multiple devices that optimize their local functions based on their private datasets. Here, Xi is the dataset of the agent I. So in my setting, we have workers that perform local steps of gradient descent, and they are equipped with photovoltaic panels. So we are back to the topic of renewables, and they have to make it with the renewable energy that they have. The data is non-IID distributed, which is the typical setting of federated learning. Periodically, the server averages the model. So what happens is that the local update is just classic stochastic gradient descent. So iteratively, we are updating the local parameters following the opposite direction of the gradient in this way that you see here. What can change usually is the aggregation method. In the literature, the first proposal was federated averaging, which is this method here, which basically does the weighted average of the model's parameters. But this has a problem, which is the fact that the solution might be polarized towards local minima if the workers perform a different number of local steps. And this usually happens in edge devices because they might have either different energy availabilities or maybe different computational capacities. So there is also another algorithm, which is FedNova, the one here, that instead of averaging the weights, does a normalization of the gradient and then performs a global step at the aggregator. To help you to visualize the difference, this one is the difference. So on the left, we have what federated averaging does. If worker number 1 does 4 steps and worker number 2 does 2 steps, the solution averaged will be polarized towards the worker number 1. Instead, on the right, you have the normalization strategy, which just divides the vector by the number of local steps that were done, and we have a solution which is not polarized. Does this work? Well, partially. This is the learning bound of FedNova. We have two parts that are important. The first one is this one, which is decreasing with respect to the number of local steps that are performed. And it's basically telling you it's good that you do local steps because you are going towards a minimum. Okay, but there is also another part, which is this one, that is instead increasing. The first term is linear and the second term is a parabola. This one is telling you, well, maybe you should stop doing local steps because otherwise you go towards your local minimum. And we want to find a global minimum, not a local minimum. So as you might notice, the terms that are increasing are weighted by eta squared, where eta is the learning rate, and the learning rate is a very small number. So what the author said is that since this is a very small number, they are negligible. We are not concerned with them, so we can do whatever number of steps that we want. Is this true or not? Well, I investigated this with this very simple example. So the function number one, these are just two parabolas, very simple example, but they have two different convexities. The goal is just to optimize the average of the two. These are the results. So on the left, you see what happens in the blue curve when one worker does double the steps of the first one, and it converges to 0, where 0 is the norm of the gradient. Also, the orange curve is still very good when the second worker does 5 times the steps of the first one, and it's also faster because we are doing more steps. But as you increase the number of as you increase the ratio between the number of steps of the first worker with respect to the second one, you start to see that actually there is a drift towards one of the two minima. And this is true even in the second case, the figure in the middle, which is a case of homogeneous workers, so where they do the same number of local steps. If it's too big, the solution will still be polarized. It's the curve in red. So what the authors say is, well, you just need to lower your learning rate and this effect will disappear, which is true. But on the other hand, you will take a long time to converge. So we want to find some solution to avoid these problems. Then what we can do is try to optimize the learning bound subject to some constraints that are the constraints that take into account the energy availability. What is important is the shape of the function that we are minimizing, because this is a very general framework. It's a framework that can minimize any function that is shaped this way. And actually, the min-max optimization often arises in telecommunications problems. The only two assumptions that we are doing is that F is convex and G is convex and increasing. The first constraint can encode a situation where the energy that we have available in a single slot is limited. The second constraint, which is an alternative, encodes instead an energy budget across the whole horizon of the learning. And finally, the last one encodes instead the presence of a battery, which evolves according to that equation that you see on the right. For this specific problem, we have the shape of F and G that are according to the part on the right. The only thing that is different between the workers is that weight Wi that you see on F, that weights in a different way the decreasing part. The problem here in distributing this problem is that the max term there does not allow you to decouple the objective function. So how do we solve this issue? We have developed an algorithm that does so. So the first step of the algorithm is that all of the workers have to locally optimize just F, which is the part without the maximum. And then they have to, let's say, send the optimal value, even though this assumption can be relaxed, to the server. And the server has to find who is the worker which is responsible for the maximum number of local steps. After this, the following step is to add G to the worker that is the maximum and see if there are workers that do not satisfy the condition of not being the maximum now. So maybe some of the solutions that we had before now are greater than the maximum because we have added G, which is an increasing function. So it cannot be, of course, an optimal solution. So what we have to do intuitively is that we have to add one by one the workers to try which is the pool of workers which is responsible for paying the G function. And ideally, that is to say that the G function, the cost of the G function, is split among multiple workers, which is equivalent to say that we increase the weight of the F function. Well, you have to iteratively add workers one by one until you reach the case where the set I, which is called the set of active function, is empty. The procedure that I explained, of course, is linear, has a linear complexity, but you can also achieve a logarithmic complexity if you do a binary search instead of adding one by one the workers. I conclude with some sample results here. The curve in orange, which is, you can say, the worst case comparing the benchmarks, is a case where we are homogeneous in the sense that all of the workers adequate to the one that has less energy. So they do the same amount of steps to make the system homogeneous. The problem here is that not enough steps are done. So the solution, the convergence is very slow. What happens if we use instead the proposal by the authors of the original paper is it's the curve in between, which is, it's a very good gain. It tells you that actually heterogeneity might help. But if you instead use the optimized solution, which is optimizing both for the number of local steps and also for the learning rate, you can have a gain in accuracy while also using less local steps. So you are also preserving a certain amount of energy or computational resources. So this ends my presentation, and I will be happy to have your questions.
Any questions from the audience? No questions? So I guess you're assuming that the messages going from the server to the workers and back are always completely reliable, right? What happens if you have an error or even a missing message? How will your algorithm be affected? Is that, a small performance degradation, or is there anything critical that may happen?
Well, if you just have one error, what can happen is that one of the workers is not able to compute its optimal number of local steps. One solution is to try to resend the value. Another solution is just go for any number of local steps because the algorithm is anyway normalizing. So what you would do is, what you would get is that you reach convergence anyway, but you maybe use a suboptimal number of local steps.
All right, thank you. Any other questions? Okay, then let's thank Giovanni here. Okay, so the next speaker is Roberto Verdone, who will be presenting online. So Roberto, I see you there. Can you say something?
Hi, everybody.
Okay, so we can hear you.
Good. I will share my screen.
Well, yeah, you share your screen.
Okay.
Can you?
Yeah, I'm doing. Give me one sec. Here it is, and this is my presentation in screen mode.
Okay.
Can you see it?
I think we're all set. Yeah, thank you.
Very good. Thank you very much. So good afternoon, everybody. Actually, yesterday I was with you in Bari, but then I had to leave for some reasons, and so I'm in Bologna now. The interpretation I gave to this opportunity to present the project I lead within the Unibo spoke, which is project number 9, industrial networks. The interpretation I gave was less of a technical nature with respect to the previous presentation. Actually, since this session is about application domains, my idea was to give you an idea of the peculiar type of use cases that we are addressing through the project I lead through industrial networks. So I will have a sort of presentation which is something in between a technical presentation and a keynote, maybe a short keynote, of course. So it will be more high level. So the title is use cases for industrial networks, and since yesterday we were told that we need to address verticals, and we need to ensure that we're going to have impact on the industry environment. I think that this is a good opportunity to me to realize how one of the structural projects of Restart can actually have such an impact. Indeed, this is one of the most vertical projects we have in the entire program. This is the set of partners who are currently involved, and the University of Bologna leads through me the project. Currently the only company who is involved, is TIM, which is however rather active in the project. The scope of our project is to support the national automation and manufacturing industry, which is one of the things that we heard also yesterday from Umberto Spagnolini, that many projects should do. So we will ensure our impact on the industry sector by supporting it for the development of 5G use cases and by supporting the standardization of 6G. So our project has both a medium term and a long-term horizon from the scientific viewpoint. So the outline of my presentation is quite simple. I will first have a high-level view on what is the role of 5G and 6G in future industrial networks. And then I will show what are the use cases that we are addressing within my project. And in particular, I will focus on one of them for the reasons that I will mention. So you see here a timeline in the upper part of my slide, which shows what is our current expectation of the development of communication technologies in industry plants, in manufacturing plants. Today, in most of the cases, automation machines are characterized by sensors, actuators, even a large number of them, and they are connected through bus, Profinet, EtherCAT, whatever kind of standard or proprietary solution that allows sensors and actuators to be connected to the controller, the local controller, the PLC, through a bus. And also the local controller is very often connected to the rest of the network, to the enterprise network through a wired solution. So the role of 5G and 6G, that I will show now, is somehow, in some cases, to cut the wire, in some other cases, to integrate to the wired network. In particular, what is happening these years, you see I'm saying 23, 24 more or less, is this is the simplest way 5G can support the development of new digital services within industries, is to connect the machines to the rest of the network via 5G. Something which most probably, and unfortunately will come a little bit later, is most probably right after the end of the Restart program, is the wide use of 5G to connect the sensors and actuators over the machines. This is an intra-machine scenario. And by the same time, we expect that also wider scenarios at the plant level where different machines will be connected via 5G will also be widely adopted. What's next? As I said, we also have longer-term visions. One of the visions that we are pursuing is the one of the remotized software-defined PLC. The idea is that the PLC, which is still currently a piece of hardware which is on the machine, should be remotized, providing a number of advantages, but I will prove later, and software-defined, making it much less expensive and more easily addressable in terms of maintenance and so on and so forth. When this will be accepted by the companies is still difficult to say, so this is why I have put here 3 question marks. For sure, this would be a very relevant step in the architecture of new communication networks for industrial networks, because when the concept of the software-defined network PLC and the remotized PLC will be accepted by the companies, it will be possible and easy to move to one step further, where the PLC will be also a centralized object, able to connect and control in a much cheaper way, much more cost-effective way, all the robots, moving robots, machines in an industry plant. For sure, this is not going to happen very soon, and so this is why I'm putting a dot on the beginning of the next decade. So when 6G will come, and for this reason, we also analyze in this course scenarios that from the technological viewpoint include a number of new technologies that for sure 6G will include, like the use of intelligent reflecting surfaces, higher and higher frequencies above 130 gigahertz, which most probably will rely on mesh networking to overcome the problems due to propagation in harsh environments like the ones with many machines in an industry plant, and so on and so forth. So this was just to give you an idea of the role that 5G and 6G will have in the coming years, in the next 10 years, basically, in industry plants. Now, my project has a WBS, which started with, as usual in projects which are vertically oriented, with our package 1, whose scope was the identification of the use cases of industrial networks, of future industrial networks, the key requirement and the key target technologies. And so what I'm going to do now is to report to you the use cases that we have selected that will be the subject of the scientific research that will be pursued in the next 2.5 years within IN. 5 use cases have been selected. I will focus more on use case 1 and use case 5. They're indicated here. These have been identified after a careful discussion with Telecom Italia and with also with external companies which are not part of Restart at the moment, that can gather to us through YLab information on the most relevant use cases for industrial networks in the future. So let me start by mentioning use case 1, which is one of the most challenging that we will consider in the project. Control to control among motion controllers for intra-factory scenarios, which means indoor scenarios, basically. What you see here is an example of a unique machine where you have a controller which gets data from sensors to take immediate decisions that have to be provided to the actuators. And this is repeated many times, as much as it is needed by the exact application. This is, in particular, what is called the motion control, as long as the actuation is used to control the moving parts of a machine, like pistons and so on and so forth. This is a very challenging type of use case, because this is a table that I take from the deliverable we just delivered, showing what are the requirements set for the wireless networks to achieve a motion control application. Just let me focus that the TI, which is basically the time interval which determines an upper bound to the end-to-end latency should be less than 1 millisecond, something which is undoable with 5G. So clearly this shows that we need 6G for this. And this is why this is a very challenged use case that we will address. And by the way, in particular, we will address something which is even more challenged, which is control to control among different motion controllers. We have use case 2, 3, and 4 that we have also set. But as I said, I want to focus more on use case 5, and I will tell you why. This is the only outdoor scenario we have. The idea is to consider big industry plants where you have many buildings. You can have drones flying over the area to manage the movement of goods, the safety of workers. You can have AGVs moving in the area as well. This is also very challenging because of the complexity of the scenario. Also, in this case, we have identified the requirements, which, depending on the specific type of application, can be delivered by 5.5G technologies. So next releases of 5G. For others, on the opposite, 6G needs to become with larger bandwidth, higher bit rates, and so most probably higher frequencies, terahertz frequencies. The reason why use case 5, I want to address use case 5 in particular, is because this will be the use case that we will consider for the Spoke Lab at Unibo that we are starting discussing currently. In fact, the idea is to use an area of the School of Engineering at the University of Bologna, which is in the square you see there. And this outdoor area will be equipped with AGVs, with drones, with several 5G base stations, programmable networks, prototype terahertz devices that we will buy off the shelf from some companies delivering these devices. And we will deliver in this area of the School of Engineering, the Spoke Lab, in collaboration with other projects that are currently under preparation at the University of Bologna. Let me conclude by showing one example of application of the use case 5, because the use case 5 might actually host different types of application. Actually, I have 3 slides here, and then I will complete, which I take from a presentation that was given a few hours ago by Lorenzo Amorosa, one of my PhD students, in the scientific session chaired by Antonella Molinaro. In this case, you see an AGV, which is supposed to bring dangerous goods. And as long as it stops, because there's a need to stop because of an obstacle, the dangerous goods have to be protected. They might fall, and this has to be avoided. So how to achieve this? Of course, you can achieve this as long as the AGV is equipped with a number of sensors. And this information is provided through the 5G or 6G network to the network and to some server where some AI will be able to predict the fact that the good is going to fall. Actually, this is something we are currently doing at BIREX premises together with Telecom Italia. This is a proof of concept that we have already delivered, but we will improve through the Restart in project, and actually is one example of application that we want to make even better in the next 2 years through the Spoke Lab we will create in Bologna. What I want to emphasize, as Lorenzo did a couple of hours ago, is that what we are doing through these use cases is to have a real vertical, and this slide is more horizontal, a real vertical consideration of the application, of the use case. In fact, the devices on the moving robot will transmit to the G node B through the RAN. And so we have to take into account the delays due to scheduling and the protocols of the RAN, which are random. And then we have the network architecture. You know that in 5G and in 6G as well, we have many different types of network architectures. NPN, so private networks, public networks, with different types of structures and so on and so forth. So even the delays introduced by the network architecture can be different. And then we have the application layer where an AI, in this case, a deep learning algorithm, has to predict based on the data taken from the sensors that the good will fall. And also this prediction takes some random time. So what we have done and what Lorenzo has shown, which is actually the result of a paper that he's going to present at PMRC next September in Toronto, is to compute the round trip time as the sum of all the elements of all the three components I've shown: the RAN, the network architecture, and the AI application, for a different number of LGVs, and taking into account all these three aspects. This is something that we are doing in order to prove when an AI application can run or not. In this case, we need to have a prediction before 280 milliseconds. And you can see that depending on the application layer, the sum of the delays in the round trip time can bring to satisfaction or unsatisfied requirement. I'm very quick on this because I want to conclude with this last slide, mentioning that this is an example of a POC that we have already performed, but this is an example of what we want to do within use case 5, within the Spoke lab that I have mentioned. It is going to be delivered, to be prepared at Unibo. We will have multiple G-Node-Bs there, at least 3, through another PNRR project. I'm buying an arena network, which allows to work in an open source context, as you know, from the Northeastern University. We will also consider more demanding applications with AGVs, UAVs, and workers in the same area that I've shown, and a number of technologies for run improvement, like the application of intelligent reflecting surfaces, higher and higher frequencies, AI-based protocol, and so on and so forth. So the general concept is that what we are doing in this project is to put together the three components that I've tried to emphasize here, are the three components that at the end will tell you, if you consider them in an integrated way, whether an application can work over a network in an industrial environment. You have to integrate both the knowledge and the assessment of the RAN, the type of network architecture, including where the computing parts are, and the AI and the application level. It's only if you account for all the three elements that at the end you can really say this is doable, and this is the recipe we have to impact on the future of the manufacturing industry in Italy.
Okay,
thank you very much.
Thank you. Are there any questions? Yes.
I can't hear, of course.
I'll repeat the question.
In the future, we want to move the PLC away from the machine. The question is why it hasn't been done until now using a wire connection. So why there should be a push for this move, with all the problems that, of course, somehow are entailed with the movement, with the change from a wire to a wireless connection, why it hasn't happened until now. It's a curiosity.
Thank you very much for the question. The reason is basically the world of PLCs is consider that there are big companies in Italy in the field of manufacturing. You know that in Italy we have the second manufacturing district of Europe after Germany, and this is why we are addressing this specific vertical, believing that Restart will have a deep impact on the progress of our country through this. There are big companies in Italy who still rely on technologies that work perfectly, who date back 20 or even 25 years. They use PLCs, they still have Microsoft XP their mantra is If it works, why should I change it? That's just a matter of mentality, okay? When you talk to companies in the field of manufacturing, in the field of automation, automation, it's not the kind of field you would expect to be so dynamic like in our domain in telecommunications we are used to be. They like to keep the same things for 20 years. And so this is the basic reason why.
Okay, thank you, Roberto. Thanks
Thank
again.
you.
Claudia, la presentazione qual è? Famiglia Battisti del Cecco. C'è più su? Okay, so the next two talks will be from the Fun Media project. So the first is going to be given by Claudio Rinaldi from CNIT about networked music performance. Claudia, keep it close.
Yes, can you hear me? Yeah, okay. So I'm Claudia Rinaldi. I'm with CNIT since April. So what I'm going to present today is really an ongoing work within the Restart project. So here the outline of my speech. An orienteering within the Restart, the metaverse, which is the main scenario envisioned in Fun Media, and various solutions for increasing one of the problem of the metaverse, which is the issue of immersivity, and finally the conclusions. So here we are. I'm within one structural project in Spoke 4, and the principal investigator is Professor Enrico Magli from Politecnico di Torino. The research context is indeed the metaverse, which does not have a common definition so far, but what we can say is that this is something that goes beyond what is augmented or virtual reality, because it tries to involve all human senses. And in particular, I'm working in work package 3. Was responsible is Alberto Bernardini from Politecnico di Milano. And with this group, we recently started a hopefully fruitful collaboration within this work package. In particular, I'm working in task 3.2, which is about advanced user interaction, with particular reference to the scenario of networked music performance. And me, which I'm CNIT, is involved together with the Image and Sound Processing Lab of Politecnico di Milano. So what does the networked music performance means? It means that we can imagine musicians geographically displaced in different places. So we want them to play together. Clearly, there are plenty of requirements in order to achieve this purpose. The main are written in the slide, so we have to give them a sense of immersivity. We have them to feel, to share the same environment. Clearly, we have to guarantee synchronization and very low packet loss. So the main research questions are, at least for me, how can we guarantee immersivity through audio processing algorithms? And how can we exploit 5G and beyond technologies to achieve this purpose? So my first answer is, okay, let us try with the spatial audio. Let us try to guarantee to these guys playing together the sensation of auralization. That is, give them a simulation of an acoustic scenario in a virtualized space in such a way that they feel immersed in this scenario. How can this be obtained? Well, there are various solutions. One is extending the traditional stereo banning, and this can be done with either an array of loudspeakers, that is loudspeakers surrounding or more than 2 loudspeakers in the place where the musician is playing, or with binaural rendering. Now, this is the example of the highest level of immersivity that can be achieved with an array of loudspeakers. Clearly, not all the musicians which are willing to play in a networked music performance have the opportunity of playing inside this sphere of loudspeakers. Look, for this kind of configuration and various other different but involving many loudspeakers, there are plenty of algorithms. Some of them are proprietary, such as one of the most famous right now is the Dolby ATmos, but there is also the Sennheiser Ambeo and so on, while others are open because they come from the research world. The same is true for the binaural rendering, which is instead a rendering solution to give the auralization, that is the sensation of being in a virtual acoustic environment to a user which is wearing headphones. In order to do this, we need to consider all the cues that our auditory system uses to understand where a specific sound source is coming from. And they are, and this is accepted, they are usually represented by what are called head-related impulse responses, which basically represent the response of our head, our torso, to sounds coming from different directions in the space. So what I've done so far is to set up an experiment, buying not that expensive head tracker. Why? I need the head tracker because I can't ask the user to stand still, especially if he is a musician. You know, I keep on moving. I'm a musician and I keep on moving. And when I'm playing, I'm involved in my music. So I need to move. And I need to follow the movement of the head of the musician because he has to keep on listening to the other musicians involved as they are coming from the same direction, even if he is moving. So I bought an head tracker. Then I've implemented the 2 different algorithms to reproduce spatial audio through headphones. One is the classical one, which basically exploits the information coming from the head tracker related to the position of the head of the musician, and every time the musician moves, this algorithm computes 2 convolutions with head-related impulse responses coming from a data set representing that have been previously computed on that specific position. I'm not describing the complex procedure to obtain this data set, but they exist, even if they are not personalized, but this is another history. And I'm also using another algorithm, which is called ambisonics, which has the great power of separating the encoding from the decoding phase in such a way that if a musician is particularly rich and he has 4 loudspeakers, quadrophonic configuration in the place where he is playing, and he wants to have this sensation of immersivity through his array of loudspeakers, with this way we can guarantee that also a musician which has 4 loudspeakers surrounding him while he's playing is guaranteed with the sense of immersivity. This is pretty hard to explain in such a few time, but yeah, I've implemented the 2 algorithms, and finally I have decided that I want to give the most of the computation to the computation burden to the network, to the, in particular, to the edge of the network, because I'm moving the computation on the network, but I want it to stay as close as possible to the user in such a way that the latency of the computation does not affect my feeling of immersivity that I've gained so early. So thanks to our partner in the Restart project, Win3, we have Mac server 100 kilometers far away from our lab, and I'm testing the two algorithms by uploading on the virtual machine on this server the spatial audio algorithm. Where we are, not that far actually, because we just started, I swear. Yeah, what I've done is to set up the virtual machine. Now the virtual machine is fine at the Mac server. The latency is 20 milliseconds, so not that good. So probably I need to fix something. And I've also evaluated the latency due to the very first algorithm that I've shown to you, which is not that much, 1 millisecond, but then I have the problem of the latency of the head tracker, which is 10 milliseconds. Now, perceptual studies have demonstrated that the human auditory system is susceptible to 40 milliseconds of latency. So I've reached the maximum and I have to try to find another solution. Shortly, I'm specifically working on these topics, but my colleagues of Politecnico of Milano are working in the same task, and we are trying to connect our research together in such a way that this feeling of immersivity can be increased. So surely what we need is to implement also the room impulse response. It is not enough to have an anechoic response if we want the feeling of immersivity. And so my colleagues are studying low complexity room acoustic modeling models because if we want to move to the network, we need to stay very low in terms of complexity. Also, they are working on the procedure of mixing and demixing along a packet switched network in such a way that a specific musician can choose what he wants to listen to with a higher volume, basically. And they are trying to do this through neural network. And finally, clearly a problem which is common to everybody who is working on network is the packet loss. And my colleagues in Politecnico di Milano are trying to solve this problem, that is recover what is lost along the network with solutions involving, again, neural networks. So, to conclude, I'm in SPOC 4, S7 for media, focused on metaverse, working on the concept of immersivity, how it can be guaranteed through audio processing algorithms, and how can 5G be helpful in this case. And there are plenty of possible answers. There is no certainty so far, but we are actively working on this. Thank you.
Okay, thank you, Claudia. Any questions from the audience? Yes? Okay.
Yes, but
Claudia.
Professor Marco Carli is asking if I have been talking about quality of experience so far. The answer is not so far, but I've just had contact with Federica, that I know she's working in quality of experience, and so we are going to start working in this. Clearly, we need the work set up to work before.
It's not a question, or rather, a comment or suggestion, maybe. I don't know if you're aware of Internet of Sounds. Is okay.
Yeah,
good.
sure.
Okay, good.
I'm in the network. You too?
Yes, but in fact, I'm not only there, but also in the architecture that you showed. So I got just the hint from Braska before. I wanted just to tell you that I saw many similarities and good topics to discuss with also those guys. So, okay, good to know.
Yeah,
Perfect.
sure.
Okay.
We'll be in Pisa. Yeah. Okay. Then I need to ask.
Okay, thank you. So what is the latency requirement for a trained ear not to be bothered by this latency?
There are studies that says that the mean is about 50 milliseconds.
50? 50?
Yeah, 50. Yeah,
That's actually
fine, fine. Clearly, maybe a trained ears maybe a little bit less, and the variance is not that small. That's the point.
So it would be an interesting experiment to see if someone who has, a well-trained ear is able to tell the difference
Yeah.
between co-locating players versus distributed players.
Yeah, I want to try as soon as possible. So if you feel like.
Right. Okay, very good. Thank you very much again.
Thank
Claudia.
you. Thank you.
So the second familiar presentation is about viewport prediction for immersive video systems. And it will be given in tandem by Federica Battisti from the University of Padua and Gioacchino Manfredi, I guess, from the Politecnico di Bari. I assume Gioacchino will start.
Okay, so hello everyone. I'm Gioacchino Manfredi from the Politecnico of Bari. I work with Professor Luca De Cicco and Saverio Mascolo, and this is a joint presentation that I will hold along with Dr. Federica Battisti from University of Padua. And these results are basically in the context of the structural project Fun Media, and in particular, the work package for authentic experience-aware content distribution. So, okay, so sorry. Omnidirectional video streaming is basically gaining ground, more and more ground in several fields such as entertainment or gaming, and it is actually it is an important feature for leading platforms such as Facebook or YouTube. And basically, immersive content is produced by capturing a scene from different angles using special cameras. And then these are played on special suitable devices called head-mounted displays, which allow users to freely explore the environment around them, and in particular, to choose which portion of it to watch. Okay, now the problem is that delivering 360-degree videos over the internet is quite difficult because, of course, it requires much larger bandwidth with respect to classic 2D videos. And in particular, also, head-mounted displays show only a small part of the whole scene to the user. So, and this part is called viewport, and now the viewport is roughly 1/6 of the whole scene. And this means that if we send the whole scene at a high resolution, this would unavoidably imply a waste of bandwidth. So now we need to find a way to save bandwidth.
With viewport adaptive streaming technique, actually we can encode only the region falling inside the viewport at a high resolution, while the rest is encoded at a lower rate. And so, as you can see from the picture, you can see that the portion falling into the user's viewport highlighted with a yellow rectangle is sent at a high resolution, while the rest of the omnidirectional scene is sent at a lower rate. And so this would allow us to save bandwidth, also because the user will never watch what is outside the viewport. Now, to save bandwidth, we need effective ways of encoding omnidirectional videos. And now, among several techniques present, the most used one is the equirectangular projection, which basically consists of projecting a spherical scene, a spherical image onto a 2D plane, so that now we can treat the video as a classic 2D video over the network until it reaches the user, and then it can be projected back onto the sphere to be correctly visualized on the head-mounted display worn by the user. Now, to actually implement the viewport adaptive streaming, it must be possible to separate the portion of the region falling into the user viewport from the rest. To do this, the tiling technique is used, which basically breaks down the frame into smaller frames called tiles. And now each tile can be encoded independently so that only the tiles falling into the user's viewport can be sent at a higher resolution. So now, the problem with viewports-based adaptive streaming, as you can imagine, is that the user's future viewport must be known in advance. And this usually is never the case. So we can only make predictions about future viewports. And the more accurate such predictions, the higher the quality of experience of the user. So its degree of satisfaction. So now, before talking about predictions, we have shown that in general, users tend to have a predictable behavior, also according to the content of the video. And in particular, at the beginning of the video, they tend to explore the environment around them to basically see where they are and what they are watching. And then they tend to follow one of the points of interest contained in the scene, whereby point of interest, we mean a specific region of the scene containing one of the most important parts of the scene. So, and now the idea is, instead of predicting the exact user's head position, let us try to predict the future viewports, the future points of interest that the user is supposed to track. And now to do this, we have considered and analyzed 6 datasets, and for each video and time samples, we have manually selected the points of interest inside it. Now notice that once this procedure is actually implemented, we absolutely need some methodologies to automatically select points of interest in a video for each video considered. So we have basically created a new dataset containing the user ID. For each video it contains user ID, the time sample, the coordinates of the user's fixation point around which we can build the user's viewport and the point of interest. Now, if you look at the picture, we can see that there is no overlap between the user's viewport highlighted in yellow and the only point of interest highlighted in red. And now we number all the points of interest from 0 on, and so we identify the exploration phase, like in this case, because we have no overlap, with -1. And now the first results in this show that on the extreme left, we can see the 2 figures that show the points of interest followed by a user in the case of 2 videos. The first one on the extreme left has just 1 point of interest identified by 0, and the other one has 4 points of interest, where -1, as I said, is the exploration phase. And what we can see is that actually users tend to explore the environment at the beginning of the video until a point of interest attracts their attention. So, and then we have taken the average tracking percentage of the points of interest for, in the case of 5 videos, and we have seen that users tend to follow points of interest for 82%, roughly 82% of the time, of the playback time of the video. So we need to understand when this happens. And so we took the average number of users in exploration phase for the case of all 5 videos. And what we can see is a decreasing trend, meaning that users tend, as we said, users tend to explore the environment more at the beginning, up to some new scarce moments of new exploration during the video. So now, before, let me just quickly talk about the DASH standard. That is a standard used in video streaming, and it actually divides the video into chunks, fixed length chunks, and then each tile of each frame in each chunk is encoded at different resolution. And then the adaptive bitrate algorithm running at the user's device keeps at least one chunk in the buffer to avoid playback rebuffering events, so playback stalls, and also selects the resolution of each tile of each frame of each chunk according to the available bandwidth. So now the idea is to leverage long short-term memory networks to predict future points of interest. So in particular, on the basis of the points of interest watched in the past k seconds by the user, the network should be able to predict the points of interest a user is likely to watch in the next n seconds. So needless to say, the higher n, the worse the prediction. So we need to find a good trade-off. And now, so of course, we need new tuning of LSTM hyperparameters for each video. And the current prediction technique is the naive approach. So it basically gives the last viewport watched by the user, basically assuming that the user does not move for the next n seconds. And surprisingly enough, this technique works more or less well according to the video. So the idea, which is still in progress, is to build a hybrid approach that combines these two approaches, so the LSTM networks and the naive approach. So I can give the floor to my colleague.
So I really feel the problem that Gioacchino has. Can you hear me? Yes, okay. So I know this is a big issue. So when he talked about this problem, my idea was, well, we can try to put the user in the loop. He mentioned quality of experience, and how can you measure that? Well, considering users. So the first thing is, what is really relevant as we are exploring a scene? Saliency. So I don't know if you're familiar with the topic of saliency. Salient thing is something that captures our attention. So if you take the image here that I brought as an example, you have a 360 image where you have a lot of people around the table with some food on. And on the left side, you have what is called the saliency map. So the warmest color are representing the points of interest, the points that attract the user attention. So basically, we know what will be interesting for a user while watching a 3D content. Well, while these studies are very well established for 2D, the same is not real for 360 and virtual reality. So the first studies date back to 2017, where there was a challenge, a big challenge in one of these conferences. And there was a big data set with 100 images, 360 images, that were displayed to 500 users inside an head-mounted display, and their gaze was tracked. And the idea there was trying to see what was really capturing the attention of the users. And there we suddenly had a surprise when we are talking, when we are seeing things in 360. So in virtual reality, we are not really exploring everything, but we are basically looking in front of us, slightly on top and on the bottom. And this is due to many things. First, because in our normal experience, so in our everyday life, we are not really moving our head everywhere, all around ourselves to watch, for example, our feet. But another important thing is that when we're wearing head-mounted display, they are heavy sometimes, till 500 kilograms. And so this movement can be heavy. So we wear a virtual reality headset and we're going to look in front of us in what is called the equator line. There is another thing that is very relevant that comes from a physiology study. So when we explore a scene, also in normal life, we are going to explore it by moving our eyes only. Sometimes we include the head movement, and very seldomly we use our torso. And this is due to the fact that this is adding some burden to our activities, and so we're not really using it. So we try to merge this at the University of Padova as research activity with what we already know. And I think you have experienced this in your everyday life. We are attracted by objects that are colored, they are very saturated, they have edges, and those are what are normally called the low-level features. But we're also attracted by things that are moving or things that are or faces, especially faces in person. And those are what are called the high-level features. So as a result, if we put together all these things that we know so far, and still there's a lot of work to do, those are the low-level features that we can extract. So edges and saturated points that are capturing our attention. We have also the high-level feature, so basically faces. And if we put all together, what we have now is an estimation of the saliency that is user-centric, that looks like this one. Now, if I go back quickly to the ground truth that has been recorded by using night tracking, you can see that we are still far from an optimal result. Let's say we have on average 75–80% correlation. So we're still working on that. And when discussing with Gioacchino and Luca, what we found is that maybe we can put together our forces. So while I'm trying to develop models for efficient salience estimation for images in virtual reality and eventually video, then we can use this to drive the viewport prediction. Because obviously what a user is doing is trying to look for something that will attract his or her attention. So this is what we'll try to do in the next future. This is something that we just started. So hopefully in next meeting, we'll be able to present some results. So this concludes our presentation. If you have questions.
Okay, thank you, Gioacchino and Federico. Any questions?
No, well, the user.
Can you?
Yeah. Yeah, so the question was, is the user supposed to move when watching a point of interest? Well, the answer is yes, they move. So the overlap must not be complete. Well, the overlap is up to a certain percentage. Of course, you never consider just the exact boundary of the rectangle around the point of interest, but you are a conservative. So you, when you transmit the video, you give the part of the point of interest watched at a high resolution, but also something around it. Also, just for this reason, because they are not still, but they tend to move. So yes, absolutely. Okay. Yes, well, we actually, these are based on dataset data, but we have not done this specifically. But we, of course, we plan to do it because it's an important information for prediction. So yes, absolutely.
I think still we don't have dataset with audio synchronized and 360. If you want, Claudia, then we can talk about it.
I see a connection between your activity and the presentation that was given yesterday about semantic communications. I don't know if you have attended it. Oh, yeah, in general for all this activity. And in fact, no, it's actually also for you, because with the semantic communication yesterday, what it was proposed to do some segmentation of image, and from that to obtain some meaning that was clearly associated with our interest in the picture. So you see any connection here?
Yes, definitely. That's exactly the same point. Finding when we're looking into high-level features, so part of the saliency is definitely linked to semantic. When I'm talking about, face detection, usually we have object detection, and it's not only faces, but okay, there are a lot of things we've done, but in sake of time, I didn't have the time to go through them. But yes, it is a part. But then in VR, we have to include, as I said, also the physiological aspect. Yeah.
Okay, very good. Thank you very much again. The next speaker is Marco Rapelli from Politecnico di Torino, presenting on the implementation of ETSI vulnerable road user awareness messages in simulated and on-field scenarios.
Okay, thanks. Yes. Okay, good afternoon, everyone. I am Marco Rapelli. I am a RTDA of Politecnico di Torino University, and today I would like to present you an ongoing project on the project Restart Move Over regarding the implementation of ETSI vulnerable road user awareness messages in simulated and on-field scenarios. First of all, I would like to start with a little insight of definitions according to the ETSI standards. You may also find here on the bottom of the slide the references of the standard ETSI regarding this. In particular, according to the ETSI standard, we have that a vulnerable road user or VRU is defined as a road user which can be distinguished between the others due to its fragility when involved in hazardous situation on the road. And the ETSI defined messages for signaling the presence of VRUs are called VRU awareness messages or VAM messages. Eventually, the ETSI defined service for the generation, transmission, and reception of VAM messages is called VRU Basic Service or VBS. So what we are trying to do in this project is reproduce a sort of VBS service. So first of all, who are our vulnerable road users? Again, according to ETSI, we have 4 main categories of VRUs, where the first category is the main one, the classic one. It's regarding pedestrians. The second one is regarding light vehicle riders, for example, bicycle riders, which can be distinguished between the first category just due to their higher speed. The third category is completely dedicated to motorcycle riders. Indeed, motorcycle riders, they do ride a vehicle, so actually they do not send VAM messages, but they send classical vehicular CAM messages, but with a special VRU container. And eventually, the last category is completely dedicated to animals, which of course do not send messages, but still are identified as VRUs when detected by sensors on the vehicles, maybe through a cooperative perception message or CPM. In this context, we will focus just on the first two categories. So in our context, we just have pedestrians and bicycles. Again, according to ETSI, we also have 4 VRU states. In particular, we may have a VRU idle state where the user is not even considered vulnerable because maybe it is inside a building or in the so-called zero risk area. So again, inside a building where there is no risk of collision, or inside a vehicle. So in this case, in the second case, the VRU will not send a VAM message, but the vehicle itself will send a vehicular CAM message. And so if we are in a VRU idle state, our VRU neither sends, neither receive VAM messages. If our VRU instead is in a so-called low risk area, so for example, a pedestrian area, in this case is in a so-called VRU passive state. So it will not send any message, but still can receive them. Of course, the two most important states are the VRU active standalone states, where we may have an individual VRU sending the so-called individual VAM messages, or the VRU cluster leader state, where we have a group of VRUs, more or less in the same proximity, electing one of them as a leader and entitle him to send messages for all the group. In this case, it will send the so-called cluster VAMs. In our context, we will not implement the cluster algorithm, and so we'll just focus on individual VAMs. According to ETSI, there is just few differences actually between vehicular CAM messages and VAM messages regarding the transmission frequency. In particular, the generation of vehicular CAM messages, of course, is depending on the motion of the vehicle, but has 2 strict limits. So in particular, you cannot send vehicular CAM messages with a higher frequency than 100 milliseconds, and neither with a lower frequency of 1 second. And those are strict limits. While instead for the VAM messages, there is not a strict limit, but just recommendation. So you may send a VAM message in any interval between 100 milliseconds and 5 seconds. The triggering conditions of individual VAMs stems from the one of the CAM messages and extend them. So here you can see that those 4 are the main triggering condition of both vehicular CAM messages and VAMs. And they all have more or less the same threshold, apart for a more relaxed time threshold, as we just described before. And all those main 4 triggering conditions are regarding a motion metric, actually a difference of a motion metric calculated between the motion metric calculated at the current time and the same motion metric calculated at the time of the last message sent. In particular, there are 3 main motion metrics, which are the difference on the position, the difference on the speed, and the difference on the heading angle. As just saw, the triggering condition of VAMs actually also extend the one of vehicular CAM messages. In particular, we have 3 more triggering conditions, out of which we have condition number 5, which is the trajectory interception probability difference between interception probability calculated at the current time and the same trajectory interception probability calculated at the time of the last message sent. And in particular, you may send a VAM if this probability is increased over 10%. There is the 6th triggering condition regarding a cluster dodging decision, which again will not be implemented, neither the 5th one. So in our context, we are not implementing the cluster leading algorithm, and at this stage of the project, neither we have a collision avoidance. So for this reason, condition number 5 and condition number 6 will not be implemented. But we implemented the condition number 7, which is the last one, regarding a proximity VAM message. So according to this, you may send a VAM message if a road user, whether a vehicle or another VRU, simultaneously is closer than a minimum safe lateral distance, a minimum safe longitudinal distance, and a minimum safe vertical distance. So basically, if a vehicle or another road vulnerable user is inside this rectangular 3D shape here in purple, which has 3 axes again, the green one, the vertical one, is fixed, while the longitudinal one in blue and the lateral one in red depends on the velocity of our pedestrian in those directions. One last thing which is worthy to mention regarding the differences between vehicular CAM messages and VAMs is regarding the dissemination conditions. In particular, according to the ETSI standard, if you are sending vehicular CAM messages with a higher frequency and then your vehicle gets stopped due to traffic or a traffic light, and so in this case, you should send vehicular CAM messages with the maximum frequency of 1 Hz. You still send actually 3 CAM messages at the higher speed, at the higher frequency before getting the minimum frequency. So for example, if your car is approaching a red traffic light and so it's moving and sending CAM messages with a frequency, let's say, of 200 milliseconds, after the car is stopped, it still sends 3 CAM messages at a frequency of 200 milliseconds before sending them at the maximum frequency of 1 second. When, of course, the car will move again, it will again send vehicular CAM messages with a higher frequency. It is important to notice that instead, VAM messages do not behave like this. So they just are influenced by the triggering conditions we just saw. So actually, what we do in this project is creating a simulation thanks to the so-called MS-VANET simulator, which is an open source simulator and emulator for vehicular networks. And you can find here the link GitHub. I will not spend too much time on this because it's quite known and used simulator in several European and national projects. So if you are interested, just go on the link here and look all the details. I will just say it is developed by Politecnico di Torino using both the Sumo simulator and the NS3 simulator. And of course, it includes a full implementation of an ETSI CITS stack for V2X simulations. So this is actually our model. Where we considered Corso Castelfidardo, which is a main avenue in Turin, which also divide the 2 parts of the Politecnico di Torino campus. And so for this reason, it has quite a lot of vehicular traffic, but also quite a lot of pedestrian traffic, because there are a lot of students actually crossing this road for reaching from one part to the other of Politecnico di Torino campus. In our simulation, we have 45 vehicles, 25 pedestrians with constant speed. So of course, it's an idle model. Actually, it's quite an early stage project, so it's fine. And of course, we have ITS messages, in particular with CAM messages sent by vehicle and received both by vehicle and pedestrians, and VAM messages sent by pedestrians and received both by pedestrians and the other vehicles. In, of course, a 250-second simulation. So focusing on just one pedestrian, we were able to keep trace of the received message, also through a Wireshark trace, you can see here, where we have both CAM messages sent by vehicle in white and VAM messages here highlighted in orange. You may see that Wireshark identifies the VAM messages with a generic BTPB protocol because the latest version of Wireshark still does not have an actual dissector for analyzing VAM messages, but still are there. Again, focusing on the same pedestrian trace, we may also identify here on the image on the left the actual trace this pedestrian go through, of course, in the simulation. And those red points here are actually the position of the message sent by our pedestrian, with also a little preliminary dissemination results with the reasons of the VAM message sent and an analysis on their periodicity. So, as just told, this is just preliminary results of an ongoing project. So we have quite a lot of future works. In particular, of course, we are envisioning of developing also a part for a more deep analysis on the simulator, also a standalone VRU basic service to develop it on our onboard unit device. And we can do this because MS-VANET simulator is based on NS3, which make it very easy actually to port our code from the simulation environment to the real world. And thanks to this, we were, of course, envisioning to have field tests on this. Maybe in a first stage with an onboard unit carried by a pedestrian with a rucksack or on a bicycle. And we may also envision a second phase where we may also develop an Android smartphone application sending BAM messages, maybe also through IMQP protocol 1.0. So in order to send messages not just in the neighborhood, but also in a so-called pedestrian to network environment. Thanks a lot. So if you have any question, I'm here to answer.
Thank you, Marco. Are there any questions? Anyone? So does your study include transmission errors, or do you rely on perfect communication here?
So we have actually a realistic channel. So
you have a realistic channel.
We have a realistic channel, yes. We are actually right now having analysis also on the collisions, because we have actually a lot of messages going on. So you see also here we have more than 100,000 messages sent and received. So we expect actually a lot of collision of this. Actually, there is also in the ETSI standard of VAMS a sort of redundancy mitigation techniques. We are not still implementing it, but we are going to. So,
okay, thank you. Any other questions? No. Okay, thanks again, Marco. Okay, so the last speaker for the session is going to be Redemptor Junior Laseda Taloma from the University of Rome Sapienza. He will present on deep learning clustering for residential behavioral analysis in water distribution systems, and this is work done under the Watering IoT Focus project.
Okay, hello? Hello, can you hear me? Hello, I am Redemptor, a PhD student at Sapienza University of Rome, and I'm working right now on as a PhD student in the Focus Project 13 WITS, specifically in the working package 1 for the design of smart water supply systems. I'm enrolled in an industrial PhD program at Sapienza Università di Roma, and my research topic is deep learning for smart water metering. My scholarship is co-financed by Regione Lazio and Unidata, and the current partners of the WITS project are Sapienza Università di Roma, Università di Catania, CNIT, but since the beginning we've started to collaborate also with Università di Palermo and Unidata itself. I have to do a little bit of introduction about water stress and water scarcity, which are the main reason for which the WITS project stands. Fresh water is let's say, designed by definition a scarce resource, because just 3% of water in the world is fresh, and just a little part of it is actually available for human consumption and human activity. So therefore is a resource that we need to take care of. In addition to this, we also have to consider that the outdated infrastructures all around the world are leaking and losing water approximately up to 40% in the distribution process. This is due to the outdated water distribution systems. The second main problem of the traditional ones is that there is no regular monitoring infrastructure, meaning that the operators need to send personnel in a walk-by, drive-by fashion to read the measurements at points. And of course, you cannot read all the points of the water distribution system because it's made by multiple nodes, I mean, thousands of nodes. And of course, so many of these readings are only estimated, and these readings are performed only periodically, which means essentially that, for instance, leaking pipes and pipe bursts are discovered only after several months, so leading to water loss and also money losses. The landscape is actually transforming in the last years thanks to recent development of IoT and low power wide area network, which are enabling the installation, the design of advanced metering infrastructures. I mean, essentially, we have long battery life IoT sensors in the form of the sensors measuring pipe flows and pressure heads at nodes that samples data, samples these measurements on an hourly basis or even multiple times per hour, and send all this to a network server where all these data are all gathered and can in this way pave the way to the design and to the application of data-driven artificial models and specifically of deep learning models. The interest in particular of stakeholders, I mean, by the water utilities and by institutions, is the possibility with data-driven models to get insights from this massive data and turn them into actions to tackle problems like like demand forecasting, user profiling, and of course early leakage detection, while satisfying, of course, the first problem that was to have a regular monitoring of consumption that was not possible before with the drive-by and walk-by approach. So once this introduction is ended, I can now dive into the main topic of this of my speech, which is the residential behavioral analysis based on clustering, and of course it relies to this third voice, the user profiling. So what I mean for residential behavioral analysis, I mean to discover the patterns, the behavioral consumption patterns of users in residential areas, I mean in cities. Why is this important to discover users that have similar consumption behavior? Because of course, you as a water utility, knowing such patterns let you to understand that the demand peaks and the demand in general that you observe on the territory, and you can also reveal by looking at the data, at the evolution of the data, to the recent demand changes with respect to the expected behavior. And as an institution, you are interested in knowing the behaviors on the area of interest, because you can promote specifically conservation habits in the community with ad hoc campaigns. And I've decided to base this residential behavioral analysis on clustering, because of course, under clustering, you can use unsupervised learning methods to automatically group the data based on some features, some similarities that are extracted automatically by the algorithm or by the models without requiring domain experts doing this job for you. Because I mean, in a large scale system, you can have thousands of users, and you cannot ask the domain experts to look at all time series one by one and label them, assigning, let's say, this consumption behavior. And the second reason to do this analysis based on clustering is to perform anomaly detection on the obtained results, as we will see in the second stage of these slides. Okay, so I show you some preliminary results of my current study, my activity with Unidata. And of course, these data have been anonymized, curated, and provided by Unidata. We are considering the LoRa smart meters data from a small Italian city. We have covered a time span of 1 year from July 2022 to July 2023. And of course, if you sample all this data on an hourly basis, you have a very long time series, which means that it's difficult to cluster such amount of time series. So I followed a well-known practice in the literature that consists in computing the average profile of each device, coming up with, for instance, that average profile for that device. So I want to cluster this 585 time series in the end. Essentially, the first thing that I did was to apply the notorious K-means algorithm, which consists, first of all, in deciding with the elbow method how many clusters you wanna get. Technically, the elbow method suggests 5, but it's not so evident as an elbow, and therefore I also analyzed 4, which reveals with the company better results. And indeed, these are the 4 clusters that I'm showing you step by step. To be clear, the color curves are just the average of all the curves ending that clusters, while the gray band is the standard deviation. So let's see this behavioral analysis by looking each of them step by step. Okay, we have 585 devices. Now we see such partition. 30% of them ended in the blue cluster, in cluster 1, that is characterized by an high peak in the morning and a lower peak in the evening. And there's not much difference between the working days and the last 2 days of the weeks on average. I mean, of course, I mean on Saturday and on Sunday. With cluster 2, you have 25% of devices of users ending there. It's pretty similar to cluster 1, with the only, let's say, exception that it seems that it starts to consume 1 hour earlier. And there's also a small increment in some days at lunchtime, meaning that maybe people of cluster 2 enter back home for lunch. Cluster 3 is more evident in the difference with respect to the previous one. They are characterized by lower amplitude of the curve, so we can think that they consume the less. And there's also a peak in the early hours of the day. And then we have cluster 4, which is the most different one with respect to the other. The first things that you can notice is that there's an high peak at dinner time, higher than the morning peak, but this is true only for the first 5 days, the working days. Indeed, the behavior on Saturdays and Sundays is different, as you can see from the shape. So there's a difference between the first days and the last few days of the week on average for cluster 4. Of course, we have performed such analysis on the average consumption, but we have considered an entire frame of 1 year, so it's reasonable also and makes sense to consider also the entire span. I just show you an example with cluster 2. Cluster 2, we have seen before the curve is homogeneous without any difference between days, and this is reflected in this calendar heat map where every single cell represents the intensity of that cell represents the total amount of water for that cluster. Of course, this has been normalized, and you can see that it's homogeneous all over the time period, with more water consumption in July at the beginning of August for obvious reason. As I said before, the second stage of this analysis opens to anomaly detection, because we can perform anomaly detection based on the clusters that I obtained before. And with just this algorithm that is essentially a standardization, this modified Z-score algorithm, that for each cluster, I'm going to compute the within cluster distance. I mean that for every time series in that cluster, I compute the distance with respect to the centroid, and now I can consider all the distances. At that point, I compute the median, I compute the mean absolute deviation, and these are the statistics that I use to perform the standardization, which is represented here in this formula. At this point, I take the absolute deviation, and if I see that the score is higher than this 3.5, it's essentially like excluding the tails of the histogram, and these are considered for that cluster as outliers. So in the end, for each cluster, I try to understand which data are the most away from the median of that clusters. So I just scroll some of these results. These are all the average anomalous profiles that I've detected with this method. And as you can see, they have different patterns in regularity, shapes, and whatever with respect to the previous average profiles that I've indeed identified. So these have, just as you can imagine, the preliminary results that I've obtained with my work in the company of Unidata. These are just, let's say, the first thing to start. I, in the end, acquired a solid know-how on pre-processing data. Of course, when you are dealing with real-world data set, especially like time series, it's very difficult to handle them because you have to construct such data set while facing many problems like duplicates, missing, noisy values, inaccurate also values, and put them in also in order because they were shifted when they provided this data to me. These first results are also reasonable and promising, then can pave the way to further investigation and in-depth investigation with, let's say, also deep learning models that can also treat more complex problems. Like first of all, the first problem is that I follow this approach in which you average all the profiles to get the average multi profiles. But of course, while doing the average, you are losing information all over the time horizon. while with a deep learning model, you can handle high-dimensional data, and therefore you can also specialize the model to tackle, let's say, 1, 2, 3 months of a specific period. And second, the most important things that I will do with Unidata in the next months will be time series segmentation, which consists in segmenting the time series in order, for instance, to understand which are the parts that differs during the evolution of the time series. So in this way also to tackle the different belonging to different clusters. So to make, let's say, a sort of dynamic clustering. So there's lots of work still to do and very promising results that I hope one day also to showcase also to you in another session. So that's all, and thank you for your attention. I'm also free for your questions. Okay.
Thank you, Redemptor. Any questions from the audience? Yes, Marco? Yeah.
Yeah, okay, you repeat the questions for the people there. Do I see some concern regarding privacy? Well, yes, of course, this was something sensible as a question, is something that has been discussed with my company. Indeed, let's say, first of all, that all this data has been anonymized. As you can see, I don't report, let's say, also the device user ID of these cures. I cannot, and also I could not even mention where this data come from, first of all. Yes, there may be some issues regarding privacy, because of course, from the point of view of the water utility, you can have for the first time access to real-time data on a large scale. And of course, let's say the monitoring personnel can see can track the habits in the end of people, and you can also understand whether the person is there or maybe in the second house, just looking at the just looking at that. So for sure, as typically done in deep learning in general, in machine learning in general, there are some ethics that we need to face. So it's for me important that something must be regulated also by the institutions, because every time that you have data, these are sensible, these belong first of all to users, and you have to be conscious as a company or as an institution what you are doing and what are the risks in this. So yes, of course, it's something that we need also to tackle, and indeed I know that industries needs also right now also to have some, let's say, personals about privacy concerns. This is now, I think, all will be mandatory.
Any other questions? Yeah. Yes.
Yeah, tell me. Yeah,
locating.
No, of course. This work in progress is just related to the behavioral analysis. But of course, the main problem for which, let's say, have been assumed by this company, let's say, put in this way, is to discover, of course, the water leakage, and because this is the problem. And this will be, of course, and the second part, let's say, of my PhD. The first thing that they want to know is this data, how they can use this behavioral analysis also for forecasting, first of all. Then, of course, we will dig deep into water leakage. Yes, of course, it will be a part also of my PhD program in general.
Any others? Okay, thank you, Lemter, then. And thank you all for staying through the end. And I'm happy to announce we're finished 15 minutes early. Okay, so you owe me something, right?
Yes, thank you. Thank you, Michele. I really want to thank you all for staying here till the end. It was a long day and actually 2 days of meetings. And I think it was interesting to see all these preliminary and results that have been obtained in the projects. I think Nicola is also connected online. Nicola, you want to say something at the end of the meeting?
Well, I hear it's very hot there, so I will not hold you further. Just wish you a nice evening, a nice travel back, and a nice summer. If I may, again, soliciting you to be more proactive, especially in hiring support personnel, not only research, but also support personnel to help you in doing this work. and ask not what Restart can do for you, but what you can do for Restart, since I am in the US. Okay.
Okay. Thank you,
Thank
Nicola. Thank you.